Well, we're going to have a fun conversation today, and we may never agree. We may totally agree. Who knows? But it'll be fun.
I doubt we're going to agree.
Okay. Paul's
We're taking your word for it, though. I don't know.
I know, but don't believe any word for this at all. Luminaries in the sky are in this toroid, and if you actually break down the motions of all the stars, they actually fit in sacred geometry patterns that match the toroid.
Lord.
So
sacred geometry of a rocket.
I'm asking you if it's real or not.
I mean, I can show you a clip from Avengers and ask you if it's real or not.
You believe that because you were told it. You never verified it yourself. Right?
And you haven't verified any of these things you're telling me. I'm in my office, and my office just has a bunch of toys in it. And so, everything behind me looks crazy. So I put this background on, but I always hate how it cuts out, like if you move.
You're okay. It's all right. Your earphones pop in now, but it's okay.
It's crystal clear.
At least you have a real photo behind you. Most people come on with a fake CGI globe behind them.
Well, this is a picture of the real globe.
That's not the globe. That's the sky.
Well, it's the bottom portion of it is the globe. You know, I mean, I didn't turn it into a wall clock, but it's still the same thing.
No, but it's not. I don't see curvature. If anything, it's convex. But you're seeing the land and the sky. That's all right. I'm just complimenting you. You have a real photo. Mm-hmm. That's all. Real photo.
Well, I'm always amazed at how many trinkets you guys can turn the flat Earth into.
Like, what do you mean? Like this?
That the wall clock behind you, the little
that's
domes.
My app. That's my app. Yeah.
Yeah.
It's just the model showing people how things might work.
Might.
All right.
All right. How about we let me try to do a formal introduction just so.
All right.
In today's episode, we'll be debating the age-old question: is the Earth flat, or is the Earth a spinning sphere orbiting the sun through space? On the Flat Earth side of the table, we have Dave Weiss, also known as Flat Earth Dave. Dave is one of the leading and most outspoken advocates of Flat Earth and runs the flatearthpodcast.com. He is featured in the 2023 film Level With Me and has made numerous appearances in news networks ranging from CNN to InfoWars, speaking on the topic of Flat Earth. And on the spherical side of the table, we have Dr. Justin Woods. Dr. Woods is a research fellow at Argonne National Laboratory, where he works jointly with the Superconductivity and Magnetism Group and the Synchrotron Studies of Materials Group. Dr. Woods studies thin film materials and multi-layered heterostructures, utilizing both X-ray spectroscopy and scanning probe microscopy. Dr. Woods holds a PhD in condensed matter physics from the University of Kentucky. Gentlemen, thank you so much for joining me here today.
No problem. Before we get started, one caveat. I'd like to state that I'm here solely in my personal capacity and not as an employee of the Department of Energy. So for this discussion, I will identify as a truth-oriented meat popsicle, not an employee of the Department of Energy.
Nice.
I was wondering if none of this can be used against you.
No, it's fine. And when I do a podcast with my brother, like sometimes people will say where they work and then email me later and be like, "Hey, can you nix that? Because I don't think my law firm needs me saying that." And I'm like, "Yeah, no problem."
All right,
that's fair. So I guess I would kind of like to get a synopsis of the flat Earth model and see what are some of the supporting precepts and compelling evidence for a flat Earth. And then we'll have some time for rebuttals and disagreements afterwards.
Yeah, no problem.
Flat Earth Dave, would you mind?
I'll just throw a couple things out. This is a balloon at 127,000 feet. The Earth is supposedly spinning 1,000 miles an hour below it. The sun is supposedly 93 million miles away. When there seems to be a local light, like it's brighter right below where the sun is. Don't ask me what the sun is. I don't know. All right. But if the sun's 93 million miles away, everything should be lit up equally. Right. When people think flat Earth that haven't really researched it, they think this, because that's what Google will serve you. This is not the flat Earth. This is a straw man image to make you laugh at flat Earth. And we laugh at it also. People say
looks like that's been altered. That doesn't look like a real picture.
Well, it's not. It's a CGI. It's the CGI image that if you Google flat Earth images, that's the first one that shows up. That's from the Flat Earth Society, which is a government-run disinformation site to make you think flat Earth is the dumbest crap ever. You know, and the comment that people say is, "Oh, are we the only pancake? Are the other planets flat?" And this is, in my opinion, two false models: a false heliocentric model, not to scale, and a false flat Earth model.
So you're telling me that there's a separate globalist flat Earth movement that's trying to take down the real flat Earth movement?
No, so the Flat Earth Society is been around for a long time, and they put a little bit of truth out there and a lot of crap, a lot of stuff that no flat earthers believe. But when you search flat Earth, Google will serve you that information first. So to us, that is what we call controlled opposition, where they feed you the nonsense. You know, when you know, one thing that's converting a lot of people to flat Earth is when they search flat Earth, they get fed pure propaganda. You know, in YouTube, like you could be searching, you know.
But I don't think you meant what you just said. When people convert to flat Earth, they're being fed pure propaganda.
No, that's what I said. That's not what I meant. When they're searching flat Earth, they're fed propaganda.
I think you said it right the first time, just to be clear. But we'll go on.
When you search flat Earth, you're fed propaganda. Like if you were searching for, you know, underwater basket weaving, how to skin a crocodile, whatever, how to grow apples. You can look up in your YouTube history and find out, oh, I watched that apple video a year ago. It's in my history. And just search, you know, whatever you search, it'll search your history. You can watch a bunch of my videos, a bunch of Jeranism videos, a bunch of real flat Earth videos, and then go search your history for flat Earth. And none of those will show up, and propaganda videos will show up instead.
Oh man, so we've already started with the algorithm is hiding this from us talk.
No, I'm just throwing that out there. You can go look at that yourself and verify.
I won't. I'll tell you right now, I won't, because I don't believe a bit of that.
All right, well, then you're not going to believe. Don't believe anything I say. I tell people don't believe anything I say. Verify everything, right? So you know when you on a flat Earth. On a globe Earth, there has to be curvature somewhere. And when we look at, you know, the ocean, it measures flat. It lies flat when at rest, not tides and waves and everything. And
yeah, it doesn't measure flat. It doesn't lie flat. I've heard you yourself say that we can see ships go over the horizon and follow the curve. This is a problem. Yeah, you have. You said it before. This is just an issue of scale. The Earth is very, very large compared to the height of a human. So what you're looking at right here is just an issue of scale. If you take a very high-powered, you take a nice camera with a very nice high-powered lens, is what I meant to say, with a nice zoom lens on it, and you zoom in on a basketball. You can zoom in far enough so that the basketball will look like a flat horizon. But if you just move it away from your face. Yeah, if you just move it away from your face, it's clearly a spherical basketball. So what you're talking about here is just an issue of scale. The problem is that in our day-to-day lives, the humans don't see enough of the Earth because of just our physical limitations and size to appreciate the curvature of the Earth in its entirety because of the scale of just the size of our stature as humans.
I get it. So the Earth is too big to see the curvature, but we can see boats going over the horizon. Right?
Because that is a physical manifestation of the curvature.
Okay. So what if I show you that there's another explanation of what the horizon is and why boats disappear from the bottom up? Would that be something you would consider?
I would consider it. I would be entertained by the conversation. Let's just put it at that.
Okay. So do you know what the curvature is at 3 miles? The globe math of curvature?
The globe math of curvature at 3 miles. Not off the top of my head because I don't need those numbers. I'm not an astro guy.
It's 6 feet. All right, and at 10 miles, it's 66 feet.
Okay, cool.
Okay, and that's your math, not mine. And so
I guarantee you didn't do the math. That's math from Physicist and or astronomer. So go ahead, please.
All right, no need to insult me. Okay,
that was an insult. It's not.
I see where it's coming from. I see where you're going.
You did not develop those theories. That's all I'm saying.
I never claimed to. I said I'm using your math, not mine. Okay, so at a 6 foot tall person, just so people understand, standing next to a perfectly calm body of water should not be able to see the surface of the water beyond 3 miles, because at that 3 miles, it's 6 foot drop. So that would be the tangent of their view. Like you can't see my mouth because it's below the tangent of this ball.
Right. Again, issue of scale there. Ball's much smaller than the Earth. Much.
That ball's smaller than the Earth, really?
Yes. I'm just saying that.
Do you think I was actually showing.
I get it.
And
I mean,
I'm showing it to scale.
It was a joke. It was a joke.
All right.
But you're making an extreme example. And go ahead
I
with your argument. It's fine.
I was showing you behind on a ball, there has to be a physical limitation of a horizon. Do you agree with that?
A physical limitation. I mean, there is a horizon. There is a horizon.
That horizon is physical. And anything beyond the horizon, below the horizon, cannot be seen.
The horizon is a physical point based on your point of observation, because that's an optics problem. Like right now, we're getting into optics and ray optics. So yes, the horizon exists at a point for me, like the picture you have behind you. Nice beach, very nice. If you're looking at the water, you see a horizon because that's the horizon at your perspective based on your height. If you were to go up 20 floors, your horizon would be at a different point at a different rotation around the curvature of the Earth. So yeah, it's a physical place, but it's dependent on your point of view and your
right. So do you realize that if the Earth was flat, the higher you go, the farther you can see?
If the Earth is flat, you should be able to see everything just as it is. Because if the Earth is flat, there should be no curvature.
All right. So I'll show you how the angle of so I'm going to show you. First, let's look at this. So this is the horizon. It's supposedly the globe Earth horizon. Now, let's say we're on a little island and there's nothing all the way around us, water's calm.
Mm-hmm.
Your limit of vision, goes to where the sky meets the ground, and that becomes your horizon. I call it your horizontal eye zone. Right? It's like you ever go to Vegas? You ever go to Vegas? From one end of the Bellagio to the other, the ceiling literally touches the floor. That's how our eyes see it, but it's not really touching the floor. It's just perspective.
No, that's a trick of optics. Yeah.
It's the limit of your vision.
But also, I think you're exaggerating that example a little bit. But I agree with that's how optics work. But the vanishing point should be above the horizon if there's no curvature. Sure.
So we're gonna talk about that. So my point is, if I'm looking forward at 12 o'clock, and whether that is 10 miles or 100 miles, I don't care. That optical horizon where the sky touches the ground would be at X distance. And at 1 o'clock, 2 o'clock, 3 o'clock, it would be at the same distance. So your optical horizon is a flat circle all the way around you. Our programming tells us that's a sphere, but reality is on a sphere and a flat Earth, you would still see in a circle. The limit of our vision is the same in all directions, so it creates a flat circle around you. So let's zoom in here. Today's consumer optics have made it so we can see farther. And as we look out here, we'll see that there's some dolphins beyond the limit of this, what we think is the horizon. And they're literally in the water. Go a little farther here. They're in the water beyond this line. Now, this is because our angle of attack is reflecting and seeing the sky, and that creates a false horizon. So these dolphins are far beyond this line that we think is a physical curve, but they're beyond it. That's just one thing, right? So let me explain that a little better.
But I also think you're underestimating. Do you know what a mirage is?
A mirage? A mirage? Well, we're seeing in the mirage. This is a mirage.
It's a form of mirage. It's a form of mirage in that when you're driving on the highway and you're on a long, flat road and you look far ahead, maybe a couple miles ahead, and it looks like there's a large puddle of water on the ground.
That's mirage. That's what you're seeing out here.
Right. What you're seeing is the refraction of light from the sky being refracted at the hotter in this case, on the road, you have a hot road so that the density of air above the road is different than the density of air off the road because the concrete gets hotter than like grass and soil. So you're seeing light from the sky refracted, not like bouncing up. It's actually refracted in the different density of the heat above the road to you in the car. That's why it looks blue, because you're actually seeing light from the sky refracted through the gradient of air densities to you as a driver. This is a similar effect. It's nothing to debunk the curvature of the Earth. It's just a trick of optics, much like a rainbow or like I said, a mirage in the desert on the highway.
Right. So we'll talk a little bit more about perspective, if you don't mind. All right.
So we just switch to topics now.
No, we're still on it. Perspective. I'm talking about the horizon. I'm going to show you how we can see farther by raising our height. So can you tell which line is the higher line?
This is, again, a perspective and scale thing.
Absolutely, 100%. And can you tell which one is the longer line? Again, perspective and scale. You know, this is good. This you got this. This is easy. So right here, this plant right here is about 5 feet above the deck. So this line is 5 feet higher than the orange line, and then the water is about 10 feet below the deck.
Okay,
and so,
again, this is a scale issue.
I'm showing you.
You've just put a horizontal line on something that's not horizontal because you're not looking at enough of the Earth. And it looks parallel. They all look parallel, but they all look horizontal. But it doesn't mean that horizon, the edge of the water back there, is perfectly flat to an infinite disk.
I'm not talking about curvature. I'm just talking about the level.
I thought we were talking about curvature. I thought that was the horizon.
Let's let him finish the point.
Right.
And then
I really haven't made a point yet. I've been interrupted a lot. All right. So what I'm pointing out here is this line is 15 feet lower than this line. So this is how our eyes see, and people have to interpret all of this, right? So going back to where we were, so here's a shot, same place, and this glossy part of the water here, just a smooth part of the water. Out here, I actually was out here in the water. This is probably 100 yards out. Let's call it a quarter mile, right? So it's a quarter mile to here, from this beach is right here, to here. That's about a quarter mile, maybe less, probably a 10, but let's just call it a quarter mile. Doesn't matter. The horizon out here where this little rainbow is, that's miles and miles out there. So perspective has, not only does it bring the sides in and the top and the bottom together, it brings the back forward. Right?
Well, can I also say something about this image? It doesn't have anything to scale what you're showing me.
What I'm showing you is, and you can do this yourself, is the foreground. You have a much better angle of attack. So I have a better graphic for it, which I got to look for.
Well, hold on. But before you move off this image, I just want to point out, like, you put your finger here, and you said it was a quarter mile to go from here to here. Yeah. But there's nothing in this picture that gives me any of that any of the perspective to make that happen. I'm just saying that like those are numbers you're saying. Yeah.
So I'm saying go out and verify this stuff yourself. Like when you take a picture, it's not as easy to show everything you mean. So this line here is the same distance, and this is just the average, as from this line to this line, and then the same distance is to this next line, and then the next line, and they all just crunch together. That's how perspective works. It's not a theory.
Right.
I mean, so it's getting crunched from together. So the same thing happens. Here's an orthographic view. So I'm standing here where you see me. I'm looking down at this ship, and if I move it out here, let's just call this a mile just for a number. The ship gets smaller. And I move it another mile, it gets smaller. I move it another mile, it gets smaller, right? Another mile, and it just gets compressed into the point where the ship will keep getting smaller, but it's not going any farther into my field of vision because I can't determine any farther distance.
But didn't you just say it was getting farther?
It is getting farther, but I can't, in my range of vision, that mile is imperceivable to me. All right. Same thing with the sky. Right. So here are those lines. The sky, this distance here is the same as from here to here. It's the same as from there to there. And then it all compresses into the horizon. So just imagine all of these lines are equally spaced. That's how we see. It's just perspective. So
okay, I see. I'm not to interrupt you again. I'm not trying to. I see what you're going with. You're saying that the reason that the curvature does not prove the fact that something disappears over the quote unquote horizon does not prove the curvature of the Earth, because you're saying that the way our vision works, so we look down an infinitely long hallway, the ceiling and everything comes together at a point at the end, right?
I'm not saying that at all. No.
That's what you were showing on those pictures, right? Everything compresses so you get farther away.
What I'm showing is that thing. I'm not talking about curvature yet. I'm getting there. This is just about how things go into and beyond the horizon. For example, excuse my horrible graphics, right? So I'm standing here. Let's say this is just a 3-foot box. I'm 6 feet tall. I can see the water. Like, let's say this is water. This is a boat, whatever. Right? I can't see the surface of the water from here to here because this box is blocking my view, right?
Okay.
On the other side of the box, you can't see. I
can't see the water, but I can see the water from here forward.
Sure.
Right? Now, if I slide that box out, the box is going to get smaller and smaller, But now I can't see all of the water in this greater area. And that greater area, I'm going to reduce it. I got the same thing. As I move the box out, the amount of area of water that's being hidden by that 3-foot box is getting longer and longer. Right?
I don't see what this relates to at all as far as like flat earth or curvature.
Boats going over the horizon. Okay. So when it's all the way out here, this line to me looks parallel, even though I'm looking down over a 3-foot box, because everything is ramped up the way we see.
Yeah.
So if
You're making the same argument. You're making the same argument that you did with the picture. You're saying that since if you look far enough into the distance, everything compacts and comes together. And this is a perspective art exercise, basically, right? When in elementary and middle school, you put a dot in the middle of a art paper, and then you draw lines to each corner, and then you draw like a cityscape, but all the angles point to that one vanishing point. That's an artificial way we can make up something like this. You're saying that as you look farther and far away, everything comes together, and therefore it's not that it passes over the curvature, that it just gets smaller, and our perspective squashes it. But what you're correct in is that everything does squash together. But the problem is that vanishing point should be a parallel line. Those the top and bottom of these images, those lines you're drawing that crunch up to come together that you were doing before, like the sky lines and the sea lines, those will crunch up and come together. And they will come together at what we call the vanishing point, the point I discussed in like art class. They'll come together at the vanishing point. But the problem is if you look at the power lines that go across Lake Pontchartrain, for instance, those power lines have a top and a bottom, and they should all, as they go off into the distance, they do get smaller because of this perspective argument you've been talking about. But the problem is after a couple miles, you see them curve over the curvature of the Earth, and those vanishing lines just keep going. Like if you were to put a parallel line at the top of each of the first power lines and just draw straight lines out, like their angle would meet at some point off in the horizon, but the actual power lines go under that and over the curvature of the Earth. Like this is kind of a roundabout way of saying, yeah, stuff disappears, but it's not because it goes over the curvature of the Earth. It's just because of the way humans see. And yeah, that's the way humans see, but it's also because it's disappearing out of your point of view because of the curvature of the Earth.
I suppose
if I show you something, good.
Well, the only other remark I'd like to add to that is the order in which things disappear as they come into perspective from the horizon. For instance, like if it's a large tanker ship or whatever coming out from the horizon, you see the top come out first, and then
because the top is higher, the bottom is the lowest point of view you have. Your angle of attack is harder and harder to resolve. I have a new graphic, and it has disappeared that it would perfectly explain that where I was heading to. For some reason, I can't find it this second.
Well, one really good example of this is if you look at I believe it's called the Turning Tower in Sweden. It's in Denmark, Sweden, and you can see it from Copenhagen. And it's there. So if I were to draw a little, like there's a body of water here, Turning Tower here, and Copenhagen's here. And because of the body of water and the fact that there's land on both sides, you can look at the Turning Tower from different places in Copenhagen. So you can just drive down the coast and be farther and farther and farther away from it. So you can do 10 kilometers, 20 kilometers, 30, 40, or I'm sorry, I think it's 10,000 kilometers, 20,000 kilometers. So like people will do this. They'll look at the Turning Tower. And the reason this is such a good example is because the Turning Tower, it looks like it's been twisted, right? There's 9 different like blocks in it, 9 different sections. And each one is twisted slightly from the X. So it makes this nice, beautiful, it's a beautiful building, this curlicue effect. And so since the building is segmented so well from a distance, you can go to 10,000 kilomiles. Listen to me, kilamiles. What am I doing? Kilometers away, and you can see that you see all 9 sections. And then you can go to 30,000 kilometers away, and you can see, I think it's 7 or 8. And you can keep going, and it just keeps disappearing. And it disappears, like John's saying, it disappears from the bottom up.
It disappears from the bottom up just for the reason that I showed you, because things get smaller and smaller, but they don't appear to go farther into your depth of field because you can't resolve that information anymore.
Because it doesn't get to you because of the curvature of the Earth.
Wouldn't the entire object itself, like if it were flat,
yeah, you can hide
the object would uniformly disappear.
It would disappear from the bottom up. It would disappear from the bottom up because the bottom, when it's out in the distance, you have the lowest view. When you look up, you have a much better angle of attack. But as it gets smaller, it all disappears into the horizon.
It doesn't disappear into the horizon. I'm sorry. What happens is the visual
like, if you look on your
information.
okay, go ahead.
I'm sorry. The visual information of the bottom of the visual, the photons that come from the sun and bounce off the bottom of the tower do not reach you because of the curvature of the Earth. That's what's happening.
So here's an example. These boats are hidden behind the curvature of the Earth, according to Globe. But in reality, they're just behind an artificial horizon, right? If you watch this boat, it's just going behind.
Well, it's going behind a wave.
It's going right. And so
I mean,
these little waves in the foreground, my finger can't hide my face, right? My finger can't hide my face, but if I brought it up here, it could hide everything. So a small wave in the foreground can hide a city in the background.
But it's not constant.
No, it's not hiding a city in the background.
I mean, like if it's a wave, it's like a temporary hiding.
Yeah, that's why you can see the boat coming
like
back
you
and coming back.
physically can't see past a certain point, right? Past the horizon, like independent of waves.
I still don't understand how this says the fact that everything smushes down as it gets farther makes it so that a flat Earth works. The only explanation for this is if the curvature of the Earth hides the thing you're looking at.
I don't understand what you're saying. No, it's hiding behind what I call an artificial horizon.
Okay, I don't think that's a thing. That's an optical. At best, it's a mirage that's playing tricks with the difference in densities of the air. But it's not an artificial horizon. It sounds like a term that sounds very official, but it's not a thing.
So here, you know what? Until I can I'm trying to find the graphic that fully explains what I was going at. But can we talk about the sun setting over the ocean or over in the distance? The sun sets from the bottom up, and because it's kind of the same thing. Yeah. No.
Sure. Yeah, it's the curvature of the Earth. It's
the curvature of the Earth.
First of all, what do you think the sun is? I want to ask a question here.
I don't know what the sun is. I don't think it's a physical object.
You don't believe the sun's a physical object?
You can see. I mean, it emits. There's some light getting emitted. Right?
Have you ever had a sunburn, Dave?
There's an energy coming from a point in the sky. If you take a magnifying glass and you focus it to a little point, like when you used to burn ants, if you lift that up a foot off the ground, that point is still there in the air, right? It puts a little fog, a little smoke, a little spray. You'll see it. It'll be in the air. I think that the sun that we see is a focal point of energy coming from a source above the firmament.
Okay.
Well,
okay, that's an interesting question. What is the firmament?
I don't know.
What is it? What is it made out of?
I don't know. I can't touch it. You can read biblical stuff that says, it's made of glass or whatever. Some people think it's made of ice. I don't know. I can't touch it. So I don't know.
So you're saying that from your perspective, the sun is breaching the source of light is coming outside of the firmament?
I think he's trying, and correct me if I'm misstating this, Dave. I believe he's saying that the sun that we see is a focal point of, I guess, the firmament focusing outside energies into the dome.
I don't know. That's just my theory. I'm not going to go there because I have no proof of it, right?
But
I have no proof of it.
Okay, but I've seen some of your videos where you talk about how I believe you said this in this movie. John mentioned Level With Me, that they would fire missiles up at the firmament. And you could see them, scrape the firmament and then explode. Nobody thought.
I did not say that. I said there has been videos where you do see it looks like something skimming across water in the sky. Again, that's what I said. Yeah.
Yeah. So if that's happening, why can't we describe the firmament to me? Why can't you describe the firmament to me?
I think that I was speaking with a NASA whistleblower, and he said that at 72 miles up, that there becomes like a thicker plasma, then it becomes water, then it becomes solid, and that's what he said. And he said that NASA has the ability, to go up there and explore, but they're forbidden, and that's all he would tell me. Forbidden by who? I don't know.
Okay, how do we have an International Space Station currently staffed by humans that will give us? Now, I know you're going to say that the live feed is hooey, but there are humans up there on the International Space Station that are looking down at a very curved ball globe Earth. And how did they get up there?
we have that. Let's finish with perspective on Earth. We want to talk about the space station. Happy to do that, right?
Yeah,
but
I guess,
go ahead.
Yeah. I mean,
Right,
if you have your video loaded on your,
there's a lot of things that you're talking about, and I just want to show you. So this bridge here, this is just miraging into the distance and curving, right?
Yeah.
It's a flat road. This is what you're seeing on the Pontchartrain power lines, right?
No.
This is the same thing. And so this guy is going to disappear into the apparent horizon, which is here. I'm going to fast forward a little bit. Well, too far. So he's just going, this is what the sun does too, right? It goes into this, right? I'll show you side by side. So here we have this is with a lens on, a solar lens, but I think I have it without it. So this is what the sun is doing. We're zoomed in on a sunset. And this guy does the same thing. He literally disappears into the horizon. Now, the ground is
he's not disappearing into horizon. He's disappearing into an optical effect done by the difference in density of air.
And that's what the sun is doing. That's what the sun's doing.
The sun is a ball of gas that emits
in a space vacuum.
Yes.
Because it's a ball. Yeah. I'm sorry. What are you saying? I don't want to interrupt. Sorry.
Okay. No, it's a ball. It's a very large ball, like an extremely gigantic ball of oxygen and hydrogen, and it's burning. It's not so much oxygen that burns off, but it does what we would love to do here in America. We do nuclear fission here, where we split the atom. There, it takes nuclear fusion, and because there's so much iron and hydrogen in there, the gravitational forces are so much that it can push all this together and create nuclear fusion. And then it's just a nuclear reactor. It's a nuclear reactor that's going to burn until the Earth. We're all long dead. The satellite here, this is going to be gone before we have to worry about that. And that gives off radiation. It's an actual object that we can study. We can track in the sky. It has a gravitational pull that works. I'm sure you don't believe that our solar system. I mean, I'm sure you don't believe that the solar system rotates around the sun, but I'm also sure you don't believe that the gravitational forces of the sun are what keeps everything in our solar system where it is, as our solar system rotates around the center of the galaxy.
So we're all over the place. You're bringing, and this is okay. You're just bringing up lots of different topics. I haven't finished one yet. One is my fault. I couldn't find what I wanted to show you.
I'm so done talking about this perspective argument because it's going nowhere.
Well, I haven't made a point yet because you keep bringing up other topics, right? And so, since you brought up the sun, that it's gases in a vacuum. What does gas do uncontained? Like if I had a jar of gas in a room that had no air, what happens when I open the jar?
Okay, again, see, you're going to make a really strange scale argument here. So if you have gas in a jar, like a high pressure gas in a jar, and you open it evaporates, right? It goes all over the room.
It finally fills the available space.
Right.
Always. So how much gas do you need before it decides to collapse on itself?
You want a number?
Yeah, I mean, do you believe that if you have a certain amount of gas, it'll finally collapse on itself instead of expand?
Yes.
Do you have any proof of that?
That's yes. I have proof of that because that's how the sun works. That's how our Earth was formed.
That's how you believe. You don't have any proof of it. You're told that and you believe it because it's in textbooks. All right, back to perspective.
No.
Here's the sun. I'm in New York City. I'm looking straight up. It's noon. It's 1 o'clock now. And so now the sun has gone beyond the building. I'm looking straight up. You see the perspective, right? You with me?
Yeah.
I'm just showing you. I'm looking straight up. So is the sun below the horizon, or is it just beyond the building? Easy question.
It's beyond the building because that's the building. That's the angle you decided to take this picture.
Let me make my points.
You asked a question. I answered it.
I know. This simple answer is all you need. All right. So this is a perspective grid, and we have a guy here. This is his eye line, and we can see this mountain is 3,000 feet above his eye line.
Mm-hmm.
Okay? You're with me. It's not in scale. My graphics aren't professional, right? And so the sun, as it moves away, it goes beyond the mountain. It's not below the horizon. It's beyond the mountain from his point of view. Correct?
For his point of view, it's beyond the mountain for his point of view, but that doesn't prove anything.
let me make my points.
I'm waiting.
Sometimes you have to wait a little longer than one sentence. All right.
Okay, but Dave, I'm going to tell you right now, I'm getting very frustrated listening to this long rant about perspective.
Because I haven't finished the point yet. So I'm trying to keep you engaged. I'm trying not to just constantly talk, and I let you talk every time you interrupt. It's fine. There's two ways that he could see the sun again. One, go up in the air. Two, go backwards. So let's go backwards. Let's say we'll go backwards 20 miles, right? So he's backwards 20 miles. He can see the sun again, because this line here, is that at his eye level, or is that 3,000 feet above his eye level?
I don't really know how to answer this, because that graphic is vastly different than the one you showed us before. You're basically just changing graphics and saying when you can see it.
When you're standing next to a building or a mountain, it's high in the air. Go 20 miles away, the top of that thing will appear to be at your eye level. I can look over New York City right now. It's 25 miles away, and those buildings, the tops of those buildings look like they're at my eye level. I know they're not, but they look like it due to perspective. Hang with me just for a moment. All right, let me make my point, and then you can
land it soon, because you're just leapfrogging over what we call the passage of time.
So the sun goes below the horizon or beyond that 3,000 foot mountain. It goes beyond it, right? It's beyond it. So now if we add the clouds, the sun's above the clouds. The clouds are also merging into this horizontal eye zone, short for horizon. And this line here is the top of the mountain is 3,000 feet above his eyes. And the mountain, the clouds are thousands of feet above the mountain. So the sun just goes away and it goes beyond this horizon. It's a physical obstruction, but it's not at his eye level. It appears to be at his eye level, and the sun just goes beyond it, like the sun went beyond the building. Globers will say this is Earth curvature, and there's no other explanation. I just gave you another explanation.
Well, how does this work in Wyoming where there are no mountains?
Because the atmosphere, even without clouds, becomes opaque over distance. I'll show you that. The atmosphere actually becomes opaque over distance.
You just said that atmosphere becomes opaque over distance, but you just showed earlier that we can zoom in and see stuff.
But wait, no. Hold on. Zoom in and see stuff locally. But when you're looking really far, it becomes opaque over distance. For example, here is good. So good. Why I'm pulling it up.
In this image, you still have the light from the side. So you're saying that the sun went beyond the viewpoint, the vantage point, but then how are you still getting light from the sun? I don't know if I quite follow.
Well, the light still day. The light attenuates. Right. The light goes out pretty far, and then the sun will take its light with it when it goes far enough away. Now you can have a light in another room behind a wall, and the light will come over the top of that wall. You'll be able to see it, even though you don't see the light. You'll be able to the actual physical light.
Right? How does that light get to you over the wall?
Well, it's lighting up I say it's exciting the gases in the sky. That's how we see the light. I mean, this sun is clearly just coming towards the viewer. This viewer isn't falling forward at 1,000 miles an hour. Okay. It's just
no. That sun is not coming towards the viewer at whatever 1,000 miles an hour you said. What you're looking at is another proof of a globe model, and it's because the sun takes a different arc through the sky at different times. So this person has just happened to be at a point in the globe where the sun is taking an arc that looks like this, and it's going to be over here. It's not going to go straight up and over everybody because of seasons. So we
can get into that, but this is the one I wanted to show you. All right. So if the Earth was spinning, the sun would go down, 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 and it would just keep on going. It would just keep on going, 15 degrees per hour, whatever they say. But when you have a very clear sky with no humidity, super clear day, usually has to be around freezing, so there's no humidity in the air. And from an elevated position, this is a drone up as high as I can get it. The sun went down, 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 and then it stopped. And it literally sat in the same spot for 10 minutes. This is super sped up, right? And so this is a super clear day. I'm super zoomed in, and the sun sat here. Now, my friends are at the beach over here. It's dark. The sun set from the bottom up 10 minutes ago, but I can still see it, right? And here's the thing. Out of focus, doesn't matter. it sat there and it stopped going down because it's going away, and then it disappeared into the soup of the clear air, and it took it with it.
I'm sorry, but I don't believe any of that. The sun, just because you have an image of the sun disappearing.
You don't believe this. You don't believe.
No, I don't. Not at all.
The sun can take its light away. So what is this? Tell me what this is.
What that is as the sun goes down over the horizon,
it stopped going down. It stopped. You have to accept the point. If the Earth is spinning, that it would constantly go down at the same rate, but it went down, 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 and when it got to this point, it stopped.
Dave, first of all, I'm gonna be very clear here. I don't have to believe this video you showed me because it can be doctored in another way.
100%. But let's say you verified that actually was film. What would your excuse be?
It would be that what you're seeing is the sunlight refracted over the curvature of the Earth. That's what a sunset is. So that's why it's like blue on the top and red on the bottom, because that's the difference in thermal densities.
You're saying the sun was going down, 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 and when it got right before it set, it started refracting. So even though it's set, it just keeps refracting. And then
I'm saying it didn't stop like that, and that looks very fishy. That looks very fishy. So
that's what the Globers said, and so I filmed it another time. They still said I photoshopped it, so I live streamed it. And they still don't know what to say, right? They're screaming and everything. You can do this yourself. You won't, but you can.
Okay, well, hold on. We talked about the firmament and gravity and everything, and you didn't want to talk about that because you didn't know anything about that.
No,
I'm supposed to believe this video.
Well, no, you're not. You're supposed to say, okay, you know what? Maybe he's not lying. Maybe I need to go verify that, but I don't think you're interested.
I think there certainly can be explanations for any optical visual effect. I mean,
like just refraction.
Well, like refraction, but that's
reflection.
Dependent
why
on
did it stop? Why did it stop going down?
I argue it didn't. I argue
so I don't know the atmospheric conditions. I don't know the atmospheric conditions in that area.
It was 32 degrees. It was super dry, super clear, and the sun.
That's over a landscape or
it's over water? It's over land, over Pennsylvania.
Okay, so you are this type of evidence completely convinces you that we don't live on a globe, but we live on a disk that is stationary and is covered by a firmament.
This is just one thing.
Okay, but you believe we live on a circular disk covered by a firmament?
No, I don't believe we live on a circular disk, and I'm not sure what we're covered by. But I do know that the nature of gas is it needs to be contained. Water needs to be contained, and biblically, there's all sorts of stuff. But I don't want to go biblically.
I mean, that can be explained very easily through Newton's law of gravitational forces. Anything, very simply put, Newton's law of gravitation means that anything that has mass will attract anything else that has mass. And that can be anything as small as a part of a molecule of water to water, or a molecule of oxygen to oxygen, aka, gases attract gases. Mm-hmm. But because in a more elaborate sense, gravity is the curvature of space-time based on a massive object pulling everything to one point. So the reason that gases don't just evaporate off the surface of the Earth is because the Earth is extremely massive, and it pulls all of those gas molecules and holds them together. And that's why we have an atmosphere. That's why we can breathe. Huh?
Yeah. So the gravity holds the gas down. And
the gravity pulls every individual molecule of air down towards the center of the Earth. And it's
stronger than the Tor 17 vacuum of space.
Yes.
Okay. And how come I can suck air and water up and away from gravity with the weak vacuum of my lungs?
Because what you are, again, I hate to keep coming back to this, it's scale. The gravitational pull of the Earth is a 1/r² law, meaning that the farther you get away from something, the less pull it has. So at the surface of the Earth, we get about 9.8 meters per second squared acceleration of gravity. That holds my big ass down here on the Earth, everybody else here. So that's fine. As you get farther and farther away from the Earth, it's weaker, which means that once you get out to the atmosphere, we don't have, it's not a consistent like air all the way up to like 10 miles. Okay.
It gets thinner
and thinner. Right. Because it has less and less pull from gravity. Right. You can even measure this in real spec for people.
But
Yeah,
gas does
escapes all
escape
the
to
time.
space.
how do you know
Helium
that?
does escape.
How do you know that? You're told that.
No,
You're
well,
told that. You have no proof of that.
how
And by
do
the
you
way,
think?
What's your proof it
Why does
doesn't?
water? Why do air bubbles rise in water? Why do air bubbles rise in water?
Buoyancy and density. Buoyancy and density.
Okay.
Okay, exactly. That's exactly the same concept.
Gravity, but just to show you, this is just I have a glass dome on a white rug, and I'm just taking a pen light, and I'm going straight across, and we'll just watch what happens. Right? This is so as I come across the light, it appeared. It goes over. So if you were inside this dome, here's your sun. No, hold on. Just watch what happens. As it goes away, it's going down, 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 and then it stops. It sits there and it fades out. And then when it comes back, the light's going to come back. The light will just fade in and come just like what I filmed.
Except I can sit down. But I can sit down and use optics and ray tracing and show you why the camera angle, your light angle will reflect off of this in a certain angle. And so when you move the light over here, you see it move, the reflection moves. But when it's moving parallel away, the reflection doesn't move. You're creating a solution to a problem that didn't exist.
Why, when the sun was going down, 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 why did it stop at the horizon?
I still don't. I'm not going to entertain your argument that it did.
Okay, so if you found out that it did, you have something to think about. How's that? Would you agree with that? That you would have something to think about. Okay, perfect.
And I'm a condensed matter physicist, and I would call up my buddy. I'd call up my buddies that were astro guys, and I'd be like, "Hey, what was this?" They're like, "Oh, that's that thing that happens when there's too much nitrogen in the atmosphere." I'd love
to hear an explanation.
But Dave, let me just say that I've given you several explanations, and you don't want to hear them. You just want to keep talking about perspective.
No, you said refraction, that it's refracting up below the horizon.
Well, that's probably the best exit. There's probably you probably saw that video. I could probably have an atmospheric geologist or somebody explain away based on a weird quirk of high and low zones in the atmosphere.
Okay. It's
definitely not that the sun stopped and moved away from the Earth, because if that happened, we'd all be dead.
Well, that's in the heliocentric world. Yes.
You don't live in a heliocentric world. No, you don't.
I don't.
Yeah,
I don't.
So like when did you change? When did you change your perspective on
when I tried to prove the globe? When I tried to prove the globe in 2014.
How did you try to prove the globe?
Yeah. I lay these experiments on me.
Yeah, I said, okay, a boat's over the horizon. That proves the globe. And then I realized that we're seeing things that are way farther than the physical limitations of a globe. And they told me refraction. And so I bought a Nikon P900 that had just come out at the time. And I went down and I zoomed in on a buoy that was over 10 miles away. And literally, it was a perfectly calm, cool day. And I'm sitting down. The camera is, let's say, probably a foot off the full ground, but let's say it was 2 feet. And I could see that buoy and I could see the water beyond the buoy, 10 miles. There should be 66 feet of curvature. So I said, curvature formula is wrong. These flat earthers got it wrong. And so I went to the debunking sites and they're like, well, you got to share the curvature. You're here and the object's here. And so it's only 33 feet of curvature, which is stupid, but okay. 33 feet of curvature. I can see a buoy that's only 10 feet tall. I'm like, how can I see that? And then I'm zooming in on all sorts of things. And then they're saying refraction. And I look at their on these debunking sites, they have a refraction slide. So you say, okay, observation height is 6 feet and the distance is 100 miles. And they're like 6,600 feet of curvature. And say, well, I'm seeing a mountain that's 2,000 feet tall. And they say, well, just slide the refractor over and you slide it until it shows up. And you go, okay, that's how much refraction there is. That's what they literally have, a magic slider that says, if you see something beyond the limitations of the ball, slide the refractor over until you see it. So somebody said, all right, you know what? Observation height, 10,000 feet, viewing height, 10,000 feet, observation, 24,901 miles away. And then you slide the refractor up and you can see the back of your head according to this math, right? So that's called pseudoscience. Did you
see the back of your head?
No, this is just their stupid calculator showing you how refraction works. And I'm showing you how stupid refraction is, how absolutely ridiculous it is.
So refraction doesn't work. Have you ever worn glasses?
Things refract, absolutely.
Okay.
But things hiding behind a physical curve don't pop up, especially things that don't have light on them.
So this is your base. Like, I'm going to be 100% honest with you. This is your whole argument for the fact that we can't have a globe, because
no, it's not my whole argument.
Well, you don't want to talk about gravity. You don't want to talk
I do
about...
want to talk about gravity. I want to get there next. Absolutely. 100%. I can't wait.
What do you think? Okay, well, what do you think gravity is? Because I guess a better question is, if we don't live on a globe, what do we live on? Are we a disc with a firmament?
No,
is it a curlicue? Is it a donut? What the hell are we talking about here?
Listen, I don't know what it is. No one knows what's below 7.8 miles. The deepest hole ever dug is 7.8 miles in Russia. And when they were using ground penetrating radar to dig that hole, they were wrong every step of the way. They're like, no more water. They hit more water. No more rocks. They hit more rocks. Right. So in the first 7.8
it does heat up. It does heat up as you get
warmer. Absolutely, it does.
So
and they hit it at
heat,
7.8.
Right?
At 7.8 miles, they hit an impenetrable barrier that they tried to get through for years, and they could not do it. They could not do it, and they finally gave up. Right. So
who is they? What's this barrier? Like, there's so many vagaries here.
This is called the Kora borehole in Russia. America and Russia worked on this. You can look it up. The deepest hole ever dug is 7.8 miles. 7.8 miles.
Okay.
Right?
Well, I agree that there are limitations in digging that deep.
Right, because there's structural, there's stress, there's issues. Pressures. Yeah, John.
And 7 miles. I mean, the crust.
All right, so what
it's a long way down before you even breach the mantle.
To answer your question is, what are we sitting on? I don't know. I think we're on the dielectric plane in between the double toroid, but I can't prove it.
What? Explain those words to me. I want you to just explain to me what you think those words mean.
So when you have a double toroid, there's a domain block wall in the center. It's a flat plane. It's an inertial plane, and I think that's where we live. That's where we live. But we're going down a lot of different things. I'm still, I'm having a difficulty finding what I want to show you today for some reason. That's my fault. But I want to show you here it is. This is it.
Dielectric plane. What?
I'll show you that in a minute. We'll go to that next. We'll go to that next. So right here, we're in Illusion, France. We're on a small
Are we doing this
mountain.
perspective again?
No, I'm going to show you curvature. So we're looking out here, and Mount Canigou is 175 miles out. From that height, the top of Mount Canigou should be well over a half a mile, closer to a mile below the curve. And you can't see it, right? Do you see me right now? No, you see the light that's bouncing off of me. I can prove that by turning off all the lights in this room, and then you wouldn't see me. So we can't see the light that's bouncing off Mount Canigou, or it's below the curve, right? But twice a year, as the sun goes in between the tropics, it lines up with the viewer and that mountain. And when it goes into the distance, we'll move the sun into the distance, it goes beyond, just like it goes beyond the mountain, beyond the building, and it backlights the mountain. Okay.
Or front lights it.
No, it backlights it. It's going behind it, right? It's going beyond. It's going beyond it, right? So it's not below the mountain, it's beyond the mountain. The top of the mountain should be almost a mile below the curve, but here it is. Now the globers say, oh, it's refracting up. The sun's refracting. The sun's already set. The mountain's a mile below the curvature. The top of the mountain's a mile below the curvature, but they're both refracting up. So the sunlight is refracting up to make us think the earth is flat. And then the non-lit mountain is refracting up and blocking the sunlight. That's retarded.
Actually, not a fan of the R word, but
all right. Well, that's slowed down mine. All right.
All right. Well, I'll say that, like, what you're seeing here, the motion of the Earth. No. I didn't say mirage. I said
this is the curvature.
Okay? Why does the sun take a different path? If there's, are you saying there's a flashlight outside of the dome that's moving around and making the Earth like that?
There's a light that spins around, that goes around, and it travels in between the tropics. I can show you that if you're unaware.
There's a light that travels between the tropics. So none of this has to do with a star that is millions of miles away that heats the Earth and sustains life on the planet. None of that works.
This is how I see the Earth. Okay, this is my model of the Earth.
This is a picture of somebody's
idea
of somebody's idea of a
so explain what's going on.
Yeah. So this is the double toroid. All of the stars, all of the luminaries in the sky are in this toroid. And if you actually break down the motions of all the stars, they actually fit sacred geometry patterns that match the
Oh,
Toroidal.
Lord.
So,
Sacred geometry.
you know what sacred geometry is?
Yeah.
The flower life. I'm sure you're aware of it, right?
I pay attention to the silliest parts of the internet as well. Okay. So
sacred geometry is silly.
how do we live on this dielectric plane? Explain that to me.
We're all electrical beings. Everything is electrical. Everything has, we have, we live in this electrical system. We are electrical beings.
So, Dave, let me ask you, how does this correspond? I mean, the whole reason why these concepts of spherical Earth developed is to be able to predict these movements of the skies, and like this animation, you can make it do anything you want.
Cool and all.
That's my opinion. That's not proof of anything. Let me ask you guys a couple questions, and this is this goes right to where we are. The Earth and all of the planets circle the sun, correct? That's in the heliocentric model. Okay, so our North Star doesn't move. Polaris never moves, right?
Polaris,
It's always where it is.
It's the North Star.
And all of the other stars circle around Polaris, but that's not really what's happening.
It's his claim to fame.
Yeah, that's not really what's happening. It's the fact that we're spinning that makes everything look like it's moving. Correct?
That's right.
Okay, so if we look at this is not to scale. Okay, trust me, I'm aware. Right. So we have our planets here, and if this is,
they're still not really to scale, but that's okay.
Of course, it's not to scale. Of course, it's not to scale.
I'm just ratting you. Okay.
So this is
neither John and I are astro guys, so we're just your pictures are fine.
So this is our pole, and Polaris is up there somewhere, right? Mm-hmm. And because we're spinning, everything goes around Polaris. Makes sense. So here's
you can't see it from the south, by the way.
Yeah. You can't see it from the south hemisphere.
Hold on. I will. I'm going to give you a reason that's fully acceptable that why you can't see it from the south. So here is Mars, right? It's pointing
that's
somewhere else.
Earth.
Well, okay. Here it is. So these other ones, their poles point in all these different directions. So Polaris means nothing to the other planets.
Yes, right? There also aren't humans on those other planets that need a North Star to navigate.
I agree. It has no relevance. It has no relevance to any of the other planets.
It has no relevance to any of the other planets, right? Here's the question I have for you. Why do all of the other planets circle Polaris? All of the other planets. Now, you're not an astronomy guy. Go verify this. Don't believe me. Go look. All of them, including Halley's Comet, everything, the sun, everything except moons. Moons go around our moon. Everything goes around Polaris.
So what you're seeing, you have a fixed point that's located, far away.
Why?
Everything is so. The North Star. You'll agree that
again, this is scale.
But
you can keep saying scale.
Let me make my point. Let me make my point here.
Absolutely.
Okay. Polaris. Earth's axis is pointing to Polaris, right? If in the globe model, the rotation of the Earth, the axis of rotation points directly to Polaris. In the globe model,
aligns very well with Polaris.
Okay.
Yeah, they said 2,000 years ago we pointed towards stupid, though, right? You're aware of that.
Well, it does change some, but not too much. Anyway,
the axis does wobble, and even the magnetic poles flip after thousands of years.
But listen to my point now. All the planets in the heliocentric model are in a two-dimensional, more or less a two-dimensional plane around the sun, and the Earth's axis points out of plane.
Mm-hmm. Right? Out of plane, correct.
So all of the other planets, if you have a fixed point, the star is far away. We're talking like light years away. Okay. And you have a fixed point in space. So if you have circles going around if you have a fixed point and you have circles, it's just like the same little I
was just thinking that the little doodly-doo we had.
Right. And in fact, in the geocentric model, which was put forth by Aristotle, but they still wanted to predict things. So they had every planet in our solar system to explain its orbits. They had these sort of orbits, these epicycle orbits. Mm-hmm. And they look just like this, and it explains. But anytime you have like a fixed point and you rotate and you have circles, this is the solution that you get.
So
it's not necessarily surprising.
We go all the way around the sun. We're pointing towards Polaris. So we're here. Polaris is over there. When we're over here, we're still pointing towards Polaris because even though we're 186 million miles farther, it doesn't matter. Polaris is so far away, you don't notice that it's not in the same spot. But all of the other planets are circling Polaris also.
No, they're circling the sun. They're circling the
sun.
Yeah.
They're circling the sun.
They all circle Polaris. They're not circling the sun. They're circling Polaris.
No. They are physically circling the sun. Polaris is another point in space, much higher than like John was saying. Much higher. Higher is a stupid word to use in space.
Polaris is perpendicular to the plane of orbit of every planet.
Yeah, that's how you get that. That's how you can stretch. I know I shouldn't put my finger in the camera. It's bad. That's how you're getting those squirrely patterns that you're seeing there. Mm-hmm. Like that's how that works, and it only works because of the motion of our planets around the sun. And the only reason, back in Copernicus was, I think, the first one to know to study that we were, a heliocentric model, because the fact that you have two things rotating is why you get things like retrograde, right? So you got something rotating around the sun, like Mercury. What's the joke? My girlfriend dumped me because Mercury's in retrograde. That's the joke. But that's because from the Earth, because Mercury's doing its own rotation and we're doing our rotation, there's a point where those rotations kind of counteract. So you see Mercury kind of like go to the other, goes back, and then it goes back again. So those things can only happen if all of the planets are rotating around the sun in their own orbit.
All I ask is that you look into how they can all circle Polaris, because when we pointed towards Thuban, they weren't going around Thuban. They were still going around Polaris. Polaris is the center, right? We are traveling in the heliocentric system. We are traveling at 4.4 billion miles a year, right? Are you aware of that?
That's a distance. That's not a velocity. Are you saying they're trying 4.4 billion?
Like the total distance.
Oh, okay. Right. Okay. All right.
So we're traveling 66,600 miles around the sun. We're chasing the sun at 500,000 miles an hour, rounding off.
It's
right. And we're doing this. That
video.
This is what we're doing in your model.
First of all, that's sped up like.
Of course, it's sped up. It's
crazy,
not
right? Either. Okay. I'm just saying. Right. Come on.
So these are
the graphic is very nice. I like
these are the motions that we're doing.
Right.
And then they also say that like 70 or 80% of the stars in our 100 billion star galaxy are binary. So you got stars doing this, trinary, where 3 stars are doing this. Mm-hmm. All of them are moving around, but never once in all of our history have 2 stars changed position due to parallax. Never once have 2 stars ever crossed each other's path. Never once.
Okay.
Well, because they all get shifted in the same amount, right?
Yeah.
So even with the swirling of our galaxy, the binary stars traveling back and forth across the sun, there is no parallax ever. Look into it.
Okay. That's not what parallax is.
Parallax is when something close it moves, so things change, right? My hand's changing position.
It's a different,
right.
But so, the rotating isn't necessarily what you're thinking.
Right. The traveling, right? So never have any 2 stars ever cross path. Something for you to look into. That's all. Right?
Well, okay. You can say that. That's fine. But what you just talked about, first of all, you're showing this diagram as if we should be like mesmerized that we're not flying off the Earth. But what we need to remember
I'm not saying that at all. It's not to scale. It's not to scale.
Well, no. But you said like we're moving at 67,000 kilometers an hour or whatever. But like motion is relative. We don't feel that those forces, because acceleration is a change in the velocity vector
or change in the vector. You're right. So if you're going 1,000,000 miles an hour or 100 miles an hour, it doesn't matter. You're not going to feel it. But if you take a turn at that speed, you're going to feel it.
Well, that's a rotational acceleration. You can either have a change in velocity with respect to time, or you can change the velocity vector with respect to time. The reason we don't feel that is because we take all this massive trip over the course of a year. So, like, if you were to go outside and get in a go-kart and do a 360 around a giant parking lot, but you did it in a year, would you feel that? Would you feel like you were thrown to the side every time? If you're turning 1 degree every month for
Just
a
to put
year.
the speed into perspective, this is the NASA rocket sled. It goes by a Mach 8.6. Can't even see it, right? Look it up on the line so you can hear the sound. It's shocking. Mach 8.6, right?
Right.
If we were in a heliocentric system, we're orbiting the sun 10 times faster than that. We're chasing the sun 100 times faster than that in curved trajectories where we're speeding up and slowing down and curving constantly. But when we go out into nature, we see things like this. And they're like, well, while all of this is going on, we have perfectly calm, stillness.
An object at rest tends to stay at rest until a force acts upon it.
We're
Newton's
turning.
first law.
Like, get a dinner plate. Go
It's
100
a
miles
constant.
an hour in a
It's a
car.
constant acceleration.
Go in. No, go in a car, 100 miles an hour, perfectly straight, calm road. Fill a dinner plate with water. Speed up or slow down or take the slightest turn, and what happens to the water?
Yeah, it's an acceleration. But you're again you're comparing magnitudes that don't match up. The magnitude of the velocity of Earth and the acceleration that's due to the rotation of Earth is hundreds of thousands of ordinals of magnitude below what you're talking about with a plate of soup. It's just they don't compare.
Neil deGrasse Tyson says that the water bulges at the equator 14 miles high.
He didn't say that.
Yes, he does.
No, he doesn't.
Write it down. Look it up.
The water does bulge a little bit.
There's a bulge.
I mean, there is
14 miles high.
a bulge.
There is a bulge.
It's getting bigger.
But I don't think it's the. I mean,
14 miles high. That is 3 times the height of an airplane.
Okay.
The
And
Earth
what is-
bulges.
what is that?
It doesn't
Why is
necessarily-
Africa
the Earth
underwater?
itself bulges at the equator.
Yeah, we're not a perfect sphere.
The Earth
We're a
itself
spheroid.
bulges.
Yeah, we're 20. I think
Do
it's
you,
what,
have
20.
do you have any proof of that?
Yeah. Well,
Huh?
how did they? Do you know the story of how it became in existence to begin with?
God created it. He pressed it like a seal in clay.
Do you have
and,
any proof of that?
created the firmament. No, I don't.
No.
But
I'm
that's the
asking you.
story.
You're asking
Right?
how do they
Your
have
Big
proof
Bang
of
story
that?
came from a Jesuit priest who made it up. A Vatican Jesuit
what?
priest that made up the Big Bang came up from a Jesuit priest who just literally made up the story of the Big Bang. Once upon a time, there was nothing. It exploded, became everything. And then all of the gases collapsed on each other and left a void, left a vacuum. High pressure next to no pressure without a container. Show me that. Show me that somewhere. And don't say the Earth, because you're assuming that there's no container. I say there is a container. Show
But
me.
you can't tell me what it's made out of or where it is or
I
what
can't
it's
touch
made
it.
of.
We want me to speculate, but show me high gas collapsing upon itself and becoming a burning sphere. You can't.
Well, it's got a lot of energy. It's got more energy than anything on Earth.
Yeah.
So show me gas collapsing.
Well, I can't show you that
Hey,
because
let's
it's not an
Hey, you guys-
earthly
Basically,
process.
You guys can come over for barbecue. I need you to bring the propane, but I don't like containers. Just bring the propane, no container, okay? Can you do
Basically,
that?
what you're asking us is to shoot you into the sun to show you how the sun works.
Well,
That's
okay.
basically the conversation here. But I guess my question is you keep asking these questions and we keep giving you answers and you keep waving them off. Well, what?
But your answers
What?
are kind of, I mean, they don't hold a lot of weight. But go ahead. But go finish your question.
It's funny you
Sorry.
talk about
Well,
weight, but don't want to talk about gravity. That's funny.
Oh, I do
like
want to
that.
talk
That's
about
actually
gravity.
fun.
Let's go to gravity. Let's go to gravity.
What do you think gravity is then? Just explain to me what gravity is.
I think gravity is electrostatics.
That's
okay.
that's not what gravity is at all.
Well,
That's a
well,
fundamental mischaracterization of what electrostatics is and what gravity is.
I'm going to show you an electrostatic experiment where you can actually do an experiment where we can manipulate things going up and down. And then you can show me one with gravity where you can manipulate it. Right?
Okay. See, I'm going to stop you there because what you're going to do is you're going to show that you can charge a ball or a feather and move it up and down with electrostatic forces that, like I have said, on a small scale at the surface of the Earth are orders of magnitude. Do you know what the fundamental forces are? Do you understand what the hierarchy of the fundamental forces are?
I can't recite them off my head, but I do know what you're talking about. Yes.
All right. So we have the strong force, which is a subatomic force. You have the gravitational force, you have electrostatic force, and you have nuclear force. So
you know the difference in the gravitational force and the electrostatic force according to your officials?
It's huge.
Yeah, it's huge. It's huge.
I mean,
because
with gravity
10
being
to
the weakest,
36.
but
the electrostatic force is 10 to 36. So
And that's why you're able to manipulate whatever charged object you were going to show me in the same field of a gravitational wave, in the same field of gravitational
that's
field.
why gravity only becomes significant when you have a large mass.
Right.
It takes a
Like
lot
the
of mass
Earth.
for it to become significant.
So,
that's why we
you know,
can't demonstrate to you a large massive object.
They just announced
or
that
gas.
I think it was NASA or somewhere. They've
Or somewhere. Really nail down your citations here.
I can pull up the video. It was just on we just had it on the hell's his name? It was hold on. It was they're talking about how gravity is how electrostatics. It was on Glenn Beck. He just had a scientist on it. He said that they're defying the laws of physics because now they can make things move with electrostatics. And in the future, cars won't need wheels, right? This is how big this discovery is, right? I don't believe any of it, right? But I believe electrostatics are a thing. So let me show you my thing. And then I'm curious on your answer. I'm curious on an answer, right? So if we where is everything moved into a different order today. So you're familiar with the 3-body problem, right?
Well, John and I have had advanced mechanics. Yes.
Okay. All right. So the 3-body problem is interesting. And, we have all of these incredible cycles that never change. Like, when there's an alignment of planets, nothing gets
hold on.
position.
Tell me what you think the 3-body problem is.
It's when you have 3 gravitational bodies interact with each other. You can't predict what's going to happen next.
Thank you. And how do you solve that problem? Yeah.
I don't know. It hasn't been solved.
You collapse it into 2 dimensions.
Okay, but we live in a 3-dimensional world. There's millions and billions and trillions of objects affecting each other. We have planetary alignments. How come the sun can hold on to Pluto but doesn't affect our moon? And
because again, I hate to beat this dead horse. It's a difference in scale. Right. The sun is a massively massive object. It disrupts space-time, and it affects mostly the order of magnitude between the effect between the sun and Pluto is much different than is orders and orders and orders of magnitude different than the effect between the sun and Pluto's moon. You said Pluto? Oh, just pick a planet. I don't care.
All right. So let me show you what I have here. We add a positive charge, it goes down. The Earth has a neutral and negative charge. Everything in the air is a positive charge. The sky is a positive. And when we add a positive charge to it, it goes down. When we discharge it, it goes back up. And you can do the same with this. And again, you're going to say scale.
Well, yeah, but what's your? I mean, heliostatics, isn't it? It's a counteracting force.
Yeah.
When we put a negative charge into this, it goes up. So here's the thing: if I can manipulate how things are I can make this is got a negative weight. It's going up, right? With electrostatics, it doesn't
have a negative weight. It has a force that's greater than the force of gravity.
Yeah.
So
it has a weight.
Okay. Everything is electrostatic. Everything. Our bodies are. Everything is electrostatics. So if we can manipulate this, we're making this go up due to electrostatics. We made that button that was hanging on those balloons. We made it go down by electrostatics. So my point is, if electrostatics are 10 to the 36 power stronger than gravity, that's a number that your mind can't even comprehend. So what is gravity? Gravity is 0 next to that. 0. 10 to the 36, right? How long is a trillion seconds? Let me ask you a question.
You're talking about the force.
I'm not talking about seconds. I'll let you make your point. Looking at this demonstration you have here, what you've done, do you see where the electrodes are?
Yeah.
You see where the electrodes are? So you've got an electrode, you've got a negative, you're saying it's negatively charged. You got a negatively charged aluminum foil triangle. I'm sure I picked this shape to make it look like a UFO.
How about this one?
Go back. Stop changing the subject.
No, because I'm
changing the subject. Go back to the thing.
This is the same thing. It's heavier, and they're flying it. This is done by MIT. It's called the Silent Drone, and it's flying off of electrostatics.
Do you know how this works?
It has no moving parts. You're going to say that it's there's airflow. There's no moving parts.
It's ionizing the molecules in the air and then accelerating them through an electrostatic field, creating a force, and every force has an equal and opposite reaction. So that's why the thing levitates.
Yeah, there's
That's
no moving parts. There's no air coming out
I
of
just
the bottom.
explained to you how that works.
Yeah, but that's how gravity, what you call gravity, works, right? We have like when lightning strikes, things go flying in the air because it reverses the polarity of the Earth for a second. Things fall at a different rate during electrical storms because the air, the sky.
Well,
yeah,
hold on. Back up. You're saying things that aren't true.
Things have been measured to fall at different
the polarity
rates
of the Earth does not change when lightning strikes.
When lightning strikes, it doesn't doesn't give it a positive charge for a split second.
The Earth?
The lead lightning is going into the Earth. Where's the energy going?
It goes out through lightning strikes the Earth like what? It's like 1,000 times a second.
There's an exchange of charge. There's an exchange of charge.
And that's why things sometimes go flying in the air. People go flying in the air when the lightning strikes right next to them. Right? That's just not defying gravity. So this thing is flying because it's changed its electrostatic charge. It's 10 to the 36 power stronger than gravity.
This thing is flying because it's taking advantage of Newton's first law, equal and opposite reactions. So this thing is the top level is ionizing the air molecules that are around the top layer. It's a large electrostatic charge, electrostatic field between two plates. Those air molecules are ionized, and then there's a electrostatic let's say a capacitor plate, electrostatic field forcing those molecules down. Therefore, if those molecules go down, the force then on the drone is up. That's how that's operating. It's not that it's being thrown up by the charge of the Earth. It is
gravity. Where's gravity?
It's still
Where's
there.
gravity?
Gravity's still acting, but you overcome
gravity's
gravity.
The thing that keeps gravity's the thing that keeps it from flying up.
It's not like you could just flip a switch here.
Of gravity. Gravity's a theory.
Okay.
Because if you turn off those thrusters, the thing falls down. That's where gravity is.
There you go.
What?
Gravity. Okay. Every force has an equal and opposite reaction. When the propulsion of that drone carries it up here, the reason that propulsion doesn't accelerate it to the roof or accelerate it off the planet is because there's an equal and opposite force. The reason that drone can hover right there in that soccer court and not fly to the ceiling is because there's an equal and opposite force.
There's a force. There's a counteracting force.
It's defying electrostatics. It's not defying gravity. Right?
You don't understand what gravity is. This is very clear.
But
gravity, hold on.
Theory. Gravity is a theory, and you can't demonstrate it.
Yeah, you can. So earlier you talked about how we have a galaxy that is flying through the cosmos. We got a sun, and we got all of our you have that great graphic where everything's corkscrewing through the universe. Like they're having a rave, right? And then you said that there's all these stars, and sometimes there's binary stars, right? Okay. Gravity, much like electrostatics, you don't get electromagnetic radiation unless you have an acceleration of charge. So you have to have a charge that is accelerated back and forth or accelerated around a ring, however, but it has to be accelerated. It can't be just a constant speed. Gravity also will generate gravitational waves when you have a very large gravitational object that's oscillating. And because, like John and I have tried to say, the orders of magnitude between these fundamental forces of nature, whether it be electrostatics or gravitational, the orders are so out of whack that you have to have a massive object that is oscillating extremely fast. And that's what you're talking about when you talk about a binary star. Those massive objects oscillating around each other at such a high rate will create oscillations in the gravitational field or the curvature of subspace. And we have detected that. That is a measurable quantity that we detected in 2015. It was theorized back in like 1893 or something like that, but it was detected in 2015. And we do that by having, again, you're gonna get upset about the scale, but we do that by having we have satellites very far away in a very specific setup. And what they can do is they can measure the oscillations in the gravitational field that they experience in real time, and they can triangulate it to what is called a pulsar, binary star.
No offense, but you're repeating stuff you've been told. You've never operated a satellite. You've never seen a satellite in space.
Actually, I have.
No, you haven't. No one's seen a satellite in space. There's no images. That's a satellite dish.
See this guy? I operated one of these at Green Bay radio station.
Yeah, but that's not the satellite. You're getting a signal.
But it was contacting a satellite.
How do you know it was contacting a satellite? You don't know what it was contacting.
How do you know I'm not a lizard person?
I don't know that. I was actually thinking
See how that argument works?
Yeah, no, but what I'm saying is you don't have proof of it. Let me ask you a question. Why is the moon and the sun appear to be the same size?
It doesn't.
No, they don't appear to be the same size.
So, okay, look, it's a happenstance. It's a happenstance occurrence. Okay.
Okay, the moon is 400. The sun is 400 times bigger.
The sun is 300 times farther away than
400,
the diameter.
400. It's 400 times bigger.
But we don't have instances where the moon appears to be larger in the sky. You know, you got this big, nice one.
It varies a little bit. It's about the same size.
So there is a variation.
Yeah. So the sun is 400 times bigger and 400 times farther. So you do believe in scaling and variance, right? Like I could show you this ball and this ball. They're about the same size, but they're not. They're not.
That's right.
Right. So that is something that we don't have to argue about. We can all agree with that. So here's the sun. Why is it so small?
Because it's
far away. So far away. That's the size. Look, if I move the sun to 1 mile over our head, it probably looks something like this, right? Forget it. You're not going to burn up. It's just a point.
My point here.
I'm just showing you something. I'm gonna prove a point here, right? And
prove my point.
All right. So if I move the sun 93 million miles away, or 8 light minutes, it's now about the size of a coin held at arm's length, right? Do you know what the inverse square law is?
Yeah,
when you double the distance of something, it's a quarter of the size, right? So
that's not the inverse square law.
It's the inverse square law goes for size and brightness. Okay.
Is it intensity?
Yeah, intensity, but size also, right? So if I doubled the distance, so this is 8 light.
The inverse square law has nothing to do with the size of
it's
the
area,
intensity.
like the area, like if you double the distance.
All right.
Yeah.
So I went from right next to us to 93 million miles away. I went from filling the entire sky to the size of a coin. If I doubled the distance, it would be about a quarter of the size. Would you disagree with that? I think it would be smaller.
I don't agree with that at all.
How much smaller would it get if I doubled the distance?
Well, I mean, what do we
double the distance from a mile?
No, 93 million miles to double that. It would be a lot smaller. And if you look at NASA, they say, what the sun looks like from other planets, and they agree with what I'm saying. So I'm just trying to walk you through something simple here.
I understand what you're saying. So
if I double the distance, it's now the size of a pencil eraser. All right. If I double it again, so it's 4 times as far, it's now pretty damn small. If I double it again, so it's 8 times as far, it's now literally the size of a star. And NASA will agree with this. Okay. If you believe in NASA. Okay. So 8 times 8, 64, we'll call it a light hour. At a light hour away, our sun is the size of a star. What if I made it 2 light hours away? Could you see it?
Well, hold on. Your definition of the size of a star is also it
appears to be the size that we see a star.
But right? Yes, because it's not our star anymore. It's not the center of our solar system.
I'm trying to make a point here. I'm hoping you can follow it. Right. So
I'm trying.
At 8 times the distance, our sun at 8 times the distance that it is the 1 light hour. And at 1 light hour away, it would appear to be like another star. If I made it 2 light hours away, I would say it would be hard to see, but let's be safe. Let's make it 24 light hours away, a light day away. You could not see it. The angular resolution limits of our eyes tells us that sun is by far magnitudes too small to see. So 1 light day away, our sun at the size it is too far for us to see. Polaris, they say, is 46 times bigger than our sun. So if Polaris was 46 light days away, it is magnitudes too far for us to see it at 46 light days away. That's not even 2 months. Let's round it up to a light 2 months, a light half a year, a light year, right? It is provably too small to see. Magnitudes over. And you know how far they tell us Polaris is? 433 light years away. And you just want to believe in your heliocentric religion that you can see it with your naked eye every night, all year long.
Well, one answer would be is that Polaris is 4.5 times the size of the sun. It's a bigger star.
It's 46 times bigger than the sun. If you followed what I was saying, I did scaling and the scaling and variance of it. And at 2 light months away, you couldn't see it. But we rounded it up to a light year, and you can't see it, but it's 433 light years away. You just want to believe it because that's what you've been told. And if you don't believe it, everything falls apart.
I
Something
feel
to think
that
about. How about this? Say that's
hold
something
on.
that you're looking
You just monologued for like 5
My
minutes
bad,
about
Go ahead,
the size of a star and said a bunch of stuff that I don't think is actually true. So let me discuss this.
Okay.
It seems to me that all of your arguments about the curvature of the Earth, where or what the hell the sun is, all boil down to what you can physically see with your eyes. Now,
I don't like looking up at the sky to prove the shape of the Earth. You wanted to go there. I would rather stay on the Earth and show you that we can measure the Earth flat. Everything about the Earth measures flat. Everything about the heliocentric system is made up as far as the measurements go.
do you have a cell phone?
Yeah.
Do you understand how GPS works?
Yeah, it uses towers. It uses towers, triangulation. When I was a kid, we had, I'm a little older than you, we had the Loran system. That's before satellites. And then they put a graphic overlay on it and said it's now being done by satellites. Think about this. You can your phone, it'll find you literally in the spot in your house, not only in your house, but you're on the left side of your house.
Pretty good.
Okay, so figure this. So your neighbor, which you have a house right next door, it can detain you. You're at your house. Your phone's not at their house, right? You have to believe that a satellite mirroring all of the spinning and whirling and twirling and corkscrewing of the Earth is somehow measuring the distance between your phone here and if your phone is over there. And with all of that, it's calculating. Now, I don't
have to imagine that. It's called a stable Earth orbit.
No, it's not a stable Earth orbit because it has to follow. Speed up.
Calculate.
Hold on, let me just finish. And then I'm sorry. Sure. Sometimes the answer takes a little longer than I'd like. I'd like to be shorter.
That's okay.
But, so we're going, and then when it's measuring, it's coming through the atmosphere. It could go through clouds. It could go through a rainstorm. It could go through dry air, weather, and that changes the speed of light. But that somehow they're able to measure it to say, oh, he's not here. He's 10 feet over there, right? That is not how it works. It works from stationary towers. This is why there is no GPS in the middle of the Southern Ocean. There is no GPS in the middle of the Amazon. People lose GPS in Arizona, right?
Okay, that's not because there aren't satellites. That's because the satellites that link to the towers you're talking about,
that's right,
are thousands of miles away. But we have what are called satellite phones that connect directly to the satellites above you and will give you your exact.
The cell phone GPS is not always contacting the satellites. That is correct.
No, it never contacts satellites. They don't even.
But there are GPS that do.
Yeah.
No,
that's why you shouldn't use your phone going out into the forest because you're going to get lost. It does rely on some cell phone towers. You're right. Yeah. However, there's also navigation ships. How do you think ships nowadays navigate? There's no cell phone towers out in the sea.
Oh, great. We got another.
Right?
We got another.
So you don't want to see any graphics? Do you want me to just chat with you?
I mean, you're saying that satellites don't exist. No, I'm sorry. That was a little bit rude of me, but you're saying that satellites don't exist, but you can't give us any other way that you can triangulate around the planet. And we have to take in, first of all, you have to take in special relativity to make GPS work because of the difference in the difference. Light takes time to move around the planet. You have to take in special relativity to make that happen, and the same special relativity that you had to take into account to measure and study gravitational waves that we have studied. These things are things that I'm sure that you don't think are even real.
You're correct. I don't think they're real. They're all theoretical, and the things that they claim are provably incorrect.
First of all, on my special relativity is calculable. I'm not
the guy to argue that because I don't know. You
can take two atomic clocks. You can take one atomic clock and I can drop it off at John's house. Then I can take another atomic clock up into a plane and fly pretty fast, fly as fast as I can. And I can bring the atomic clocks back down and I can compare them and they will be different. That's an experiment that's been done.
Yeah, I don't know. That's not my expertise, right? That could do with the ether. I don't actually know the answer to that, so I'm not going to speculate.
Your argument about the towers, the triangulation. I mean, there are no cell towers out in the sea, right? So how does the GPS work there?
So are you guys familiar with the Satelloon program?
This sounds made up, but go for it.
What is this? What is this?
Sounds made up.
No,
It sounds-
what you ask about? I didn't hear it.
So the Satelloon program. So NASA launches satellites mostly from Antarctica, but all over the place. There's tens of thousands of these things. They weigh up to 8,000 pounds, and they can control where they go. There's tens of thousands of them in the air. They admit it. NASA controls 99% of the helium on Earth. You can't get helium in a large quantity unless you go through NASA, right?
And so I don't think so.
You can get helium from air gas.
No,
Justin and I have both
listen,
ordered
NASA
large quantities.
Large quantities like a stadium full, right? Some of these satellites, some of these satellite balloons are bigger than football stadiums.
Hold on. That's gaseous helium. John and I can definitely give you a stadium full of gaseous helium. We were saying that we dealt with liquid helium. And
the volumes expand
exponentially. So yeah. And you buy that from air gas, the same place I buy the CO2 I use to run my kegerator. So it's not, NASA is not throttling.
They don't have a monopoly on helium.
Yeah,
that is not true.
So we'll skip over that then. All right, I retract.
So we just change the subjects.
No, I disagree with that, but I'm not. I don't have. Well, it's admitted NASA controls 99% of the helium in the world.
It's not.
Okay, I said we'll skip over it because it's pointless right here. So you guys have seen Starlink go by, right?
Sure.
Have you ever seen it yourself? I have. It looks just like that. It looks just like that, right?
Well, I mean, I've seen the. You can see it from the ground. Yes.
Yeah. You're making my point. So we can see it from the ground. Do you know how big a Starlink satellite is?
Well, they're reflecting the light from the sun.
Mm-hmm.
Okay. So they
don't produce their own. It's a huge
light from our cities and things.
This is a 747.
Okay.
All right.
That's right.
And when you look, it's hard to see in the picture, of course, but you can see the shape of the plane, but you can't really make out the engines.
And they don't have solar panels.
Yeah.
Solar panels absorb light. They don't.
They're not completely.
So you think that no matter how small an object is, it can reflect light forever. Light spreads out.
Have you ever seen a mirror far away, like a quarter?
Yeah. So let's talk about that.
If it's hitting sunlight in your face, you'll see it.
Listen, you got to let me make my point, but I'm going to I got to address your point, John. Right? If you had people, you guys were out in a field somewhere, and I'm way up in the air, and I got a mirror, I can only reflect it at you, John. I can't reflect it at both of you at the same time if you're separated. Right?
Actually, depending on the shape of the mirror, you can.
Yeah. Well, so when we see the satellites go, they're not flickering. They're like lights. I don't know what those are, but I'm going to prove to you that it's not a Starlink satellite. So this is a 747, and you don't even notice this is about 7 miles high, and there's a Starlink satellite. They keep not really giving us the specs on how big it is. I say it's the size of a human. Let's say it's the size.
That looks like a big mirror to me.
Let's say it's the size of 5 humans. If it was a big flat mirror, then it would only reflect that one person at a time, right? You can't even see this guy standing here next to this engine. So let's say we can fit 5, 10, 15, 30 satellites inside that engine. Let's say 5, just right. So it's a fifth of the size of this engine. Okay. Do you know how high the Starlink satellites are? 350 miles up. And you think you can see that with your naked eye? You're lying to yourself if you do.
It's shining a big flashlight in your face.
Yeah.
So people can see it all over at the same time. And that flat surface is shining at everyone's eyes at the same time. Try that. Get a solar panel and flash it on 2 people that are standing 20 feet.
But the distances. Anyway, go ahead, Justin.
You just said, John. You just and Dave. You just said light spreads out. So if you have something that is reflecting light, it's going to reflect it into a cone, and several areas might see it at the same time. Also, the other thing is nobody is showing that during the day because the relative radiance of light bouncing off Starlink is going to be much harder to see during the day than at night. I mean, sometimes you can see satellites and things in the day if it's atmospheric conditions willing.
These are beliefs. I've seen these things that we think are satellites. They're lights in the sky. I don't know what they are. They could be human technology. Or not. I don't know. But they're not what they tell us, and that's provable by the size and the fact that they don't flicker. I saw the ISS. I tracking it. I'm like, it's going to rise in 2 seconds, and bam, there it was. And it went across the sky at 17,500 miles an hour. I'm still looking at this thing, and it's 3,000 miles away. Like, how is it even possible? How can I see something 3,000 miles away?
Because it's a big thing that reflects light, and the fact that you can, it might be
fact that
moving.
you can't move something and have it reflect light on everyone at the same time. When
The
you
moon
reflect
does.
here,
Yes, it does.
no. That's the moon
Yeah, it
is
does.
its light. The moon is its own light. Okay,
No,
No, it's not.
the moon is its own
it's
light.
on its own light.
All right,
And then-
you're not understanding that. But here, let's go back to satellites for a second.
I'm understanding a lot, Dave. I
You're
just
not-
want to be very clear here.
You're not understanding how a reflecting light off of a shiny surface works. Go get a mirror and try to reflect it on a whole bunch of people at the same time. You can't do it.
Well,
you
we're
can't-
not 300 miles away either.
Yeah, and it's called a concave. You could do it. It's also called a disco ball. That happens. But you can actually have a flat mirror, like John said, 300,000 miles away, and it makes a large cone of light. The International Space Station, which we have humans on right now, that will call you up probably if you ask them to do a podcast with you. I don't know if they'll take that call.
We've tried. They won't. But I want to let's before we run out of time. I'm going to show you the astronauts faking being in space. If I show you them faking,
this is good.
Would that be enough?
Yeah, do it. Let's go.
Okay. All right.
Let's hear it.
Wait, last thing on satellites. Where does the satellites get its electricity from? It needs power to transmit and stuff. Where's
Solar
it getting?
panels.
It's getting it from its solar panels. Do you know what kind of solar panels they have on there? You know how much power? You know how much power? If these solar panels were 100 times stronger than the best ones we know about, they wouldn't have enough power, right? You're just making it up. And where are the solar panels grounded? How are you grounding it? Where's the grounding coming from? It's grounded into space.
No, it's ground to the battery that they charge.
No, that has to be grounded to work, right? And
it doesn't.
Yeah, no,
it's a safe.
Yeah, we could have. I taught a class on semiconductors a couple semesters ago. I could go through with why they don't have to be grounded, and you're grounded to the negative terminal of the battery, so they can charge the battery when they're not being used during the day. I'm going to ask this question. I don't think you have an answer. What is the wattage use of a satellite during the day?
I don't know the answer.
You know that? Okay, then how do you know that it doesn't generate enough power to power the satellite?
So the cell phone, like a cell phone tower, they use a lot of electricity.
That's connected to a power plant.
So if a cell phone tower was 5 miles high, it would have a nice big radius, right? It would have a much bigger surface area, right? The higher the tower is, the better surface area, right?
Mm-hmm.
Okay. Well, what has all the equipment for picking up signals, transmitting signals, Wi-Fi, everything, airplanes have that power, have that on them already. So all these satellite phones is they're connecting with airplanes. Those airplanes are relaying them to a ground tower, and they're connecting. If they're not doing that, they're irresponsible.
That's not true.
That is true. Look into it. So here's a rocket that's going to go to Mars. By the way, this thing is so big you can drive.
I just want to point out we changed subjects again because you couldn't
and
explain
that
how much
doesn't
power.
imply that we agree with that. I mean,
Just because we changed subjects doesn't mean we agreed on what you just said.
We agree to disagree. That's fine. And
fine.
I want to talk about.
But also, just real quick, satellites do not. We do not communicate with satellites. Scientific satellites using Wi-Fi and shit. We use that microwave radiation. That's why we can still. We're beaming stuff.
Do our cell phones use satellites?
Depending on what cell phone you're using, I mean, they use it for GPS, and then generally, if I call John right now, it's not going to bounce off a satellite. Likely, it's going to go through a relay of towers.
But sometimes it does.
If you're in the middle of the ocean and you have a satellite phone, yes.
I claim that they connect with airplanes, and it's like during the Ukraine
why
war,
am I supposed to turn my phone off when the airplane is landing or taking off?
Because that's a great question. Why I never do, by the way, and they never. So moving forward, because when you have to tell me honestly if you think this is real or not. Okay, this thing
is that a real image? Yes.
Okay, is this a real rocket? Let's see. Now watch. And now we're going to have different shots.
I mean,
we have an onboard. And we have a rocket. We have a camera on the ground. Right.
What are you showing us here?
I'm showing you a rocket going to space.
A rocket.
Okay, I'll tell you what. I don't see any boosters. I don't see any.
Okay.
So unless it's a solid rocket booster with no people on it.
Look at the smoke coming out of here. How fast is that moving? Now look at the difference in height. The onboard, right? Now this is falling. This is over 10 or 20. So no, it's on its way down. It just went up and now it's coming down. It's going to land.
So
it's going to land.
There's no context for this video. Is this a SpaceX test?
I'm going to get to that. I just want your honest. I don't want to give you context because I want your opinion. Okay. And then I'll give you the context. Look at the speed of the smoke coming off of here. Is this thing free falling? But now look how high it is. All of a sudden, this is not out of order.
These are two different images.
Okay.
I mean, this is
clearly not real. Okay. Now this is falling. Now look how high it is. Right. And now watch. The three engines are going to turn on. The cameraman's going to, with an edit, get right underneath it. And it's going to burn out. Two engines are going to burn out. Look, three engines are lit. Two of them are going to burn out. Okay. 1, 2. And now with one lopsided engine, it's going to land upright with a whole bunch of smoke and land right where it was supposed to land. Is that real?
I mean, whether it's real or not, the fact that you showed me an edited image of a rocket and won't tell me
real or not.
I mean, I can show you a clip from Avengers and ask you if it's real or not.
The Avengers clip is better than this. This is a real Elon launch. This is the
there you go.
That's going to Mars. Yeah, but so now you believe it's real, even though what you just saw is ridiculous.
We could have an entirely different podcast about what I think about Elon Musk and his rocket science. But they are launching rockets. Clearly edited. That was clearly edited to make it look.
What was edited to make it look what?
Oh yeah, it's like high, low, falling.
No, that was them. I literally I cut out some stuff in the middle, but
you're not talking to the guy that's going to defend Elon Musk. Just FYI.
Yeah, I didn't take anything out of context. I didn't take anything out of order. Right.
So, all right. Are you asking me if Elon Musk has sent rockets up into space? Yes. Do I think Elon Musk is kind of a weird dude and we can have another podcast about that? Yes. I'm not saying like this video doesn't say anything about whether the earth is flat or round. It's just a video of a rocket going up.
I'm just saying that they're faking space and no one's ever been to space because space is fake.
But I mean, tell me what's happening here and see. You can go to a rocket launch.
So that's a whole nother thing. Okay.
All right. Well, but just show you that you can.
You can go to a rocket launch, but you're not seeing what you think you're seeing. Yes, sometimes they launch a rocket, but there's a lot of helium involved.
I see the sonic booms over my house all the time.
What's going on here? Where did that guy come from?
That was two cuts of video together. It's not.
Watch here. This was the live feed, and he just came in like that. This was during a live feed. He just appeared, and this guy disappeared.
Okay, Dave, what you're saying is
during a live stream, when they're doing a live stream and you see this happen, would that make you question whether you're seeing reality?
If that's a live stream and watching it on YouTube, yeah, I'd be like, oh, they messed up the video. I wouldn't think about
they messed up the video. Is that what you would believe?
Well, I don't believe you because you're showing this video that could be very well edited.
Absolutely.
And you don't believe gravity is real.
This is all from NASA. This is from their live streams, and you can go verify this stuff yourself. The problem is people don't want to go verify anything. Here's from, this is from, I think this is the Chinese space station. Watch this cord. Where's it going? It's going.
It has a mass and it's leaning towards the Earth.
Yeah, but why is it going? What's this line that's going in? There's a layer here. Look, watch. What's going on there?
Oh, so
this is manipulated. Okay. This is fun one. This is
forward.
This is
can I ask you a question, Dave? You're going to show us video after video after video that's going to have some kind of this is very much Alex Jones, Anderson Cooper's nose disappeared type stuff.
Really?
What? Yeah. This is very much Alex Jones, Anderson Cooper's nose disappeared kind of stuff. What do you get out of this? What do you get out of doing this?
That's a good question. I will tell you why I do this at the end. We're almost done. All right. So have you ever seen bubbles in space where bubbles are going all over the place? They just happen to do all of their testing. They have a model in a pool that's where they test everything. And in the pool, they have green screens. And in here, this space shot, looks like a scuba tank to me.
And I'm guessing we didn't go to the moon.
Is this like the test chamber video feed? I mean, because they do test in pools, but they do test.
But they were this is something that they're showing in space, and it's weird. But, I don't know the protocols. They
we're
got
taking your word for it, though. I don't know.
I know, but I say don't believe anything.
Word for this at all.
I tell you, don't believe anything. You can go verify this stuff yourself, but you won't. You put they got their shoes on.
You don't know.
Maybe you will. Maybe you will. Maybe.
But I would have to verify it.
So they got their shoes on the wrong foot. Is that what we're saying here?
Yeah, that's weird. That could just be an accident. Let me ask you a question. Why doesn't his spacesuit explode? He's got high pressure in there.
It's very constrictive.
It's very flexible. It's like a snowboarding suit, for Christ's sake. He should explode. He should explode.
But you control the pressure. You control the pressure. It's the gas is in a container as you were
you're in the suit,
and you reduce the flow rate.
Right. So he's got gas in there. There's
okay. Let me ask you this.
There's zero pressure outside. Hold on. Zero pressure outside. How many times has NASA put an astronaut in a vacuum chamber on Earth? How many times?
That would kill a person.
Once. Well, no, in a spacesuit. In a spacewalking suit.
I don't work at NASA.
They did it once and they almost killed him. They did it once and they almost killed him.
I don't believe that at all.
Okay.
Well, Dave, there are many high vacuum high vacuum chambers that have vacuums comparable to outer space, and there's just leak valves that they don't. The chamber you don't put if you flow a gas to a vacuum chamber, the vacuum chamber doesn't explode. Yes, gas just slowly infiltrates.
In a vacuum chamber, put they put, I think it was Stretch Armstrong doll, and it exploded. In a vacuum chamber.
Well, if you flood it with pressure, if it
you suck all the air out, it explodes.
Right, because the skin of the Stretch Armstrong doll is latex rubber. It's not the reinforced flexible.
What's going on? Yeah, what's going on here? Look at his hair.
Again, you just keep changing the subject every time
because I can show you everything. You have an excuse for everything. Look at the wire going right through his hand. Is that real? Is that real? Now, you're going to say your only answer is
he just missed his hand.
It goes right through his hand. It goes through his hand.
But I mean, again, even if that was on Earth,
Alex Jones. This is Alex Jones.
Why are you saying that's Alex Jones? I'm showing you.
It's Alex Jones. Anderson Cooper's nose disappeared stuff. This is just video compression errors or something like that. This is not
compression errors. That's what this is.
Are you telling me a wire went through a man's hand?
No, I'm telling you that it's not real. That it's not real.
Dave, that doesn't even make sense on Earth. Like how, right? I mean, that doesn't have anything to do. The
wire is not real.
So it's obviously a digital artifact in the video.
Yeah.
It's just a digital artifact.
Like whether even I'll give you this. Even if that was filmed on Earth, you would admit that's not real, right? Oh shoot. I think okay.
No, you're good.
So here is this is
Dave. I'm not interested in just watching your cherry picked videos about.
I mean, there's thousands of these. Here, just tell me what's going on here. They got a fresh lemon on the space station, right? And they're playing with their food, right? Is this a real lemon? Watch what happens with this lemon when this astronaut grabs it. I'm going to zoom in so you can see it better. Here it comes. Okay. Watch again. It goes.
It was a pixelation on the image.
Oh, that's pixelation. Look at the hand.
Watch, you can see the squares.
You can see the squares.
There's a square there, Dave.
Why is
you can see the squares? They're very rigid.
Yeah.
You guys are probably just in denial, man.
Keep showing the video you want to show. That's fine. Okay. Keep running the loop. I want to know what you get out of this. Like, I want to know what you get out of this because in my opinion, and I have a question you can answer or not answer. And because I have an answer to it, John and I have regular 9-to-5 jobs. Do you have a regular 9-to-5 job?
I used to have my own company. I was making a ton of money. I was actually doing extremely well. And I walked away from it all because this is the most important message that needs to get out there. We need to wake people up from the heliocentric deception because that's how they get away with all the bullshit that they're getting away with. People are lost in space, spinning out of control. They're hiding creation. They're hiding where we are. They're hiding more resources. They're hiding more land. They're hiding everything, right? And they're hiding our divinity. They're hiding the fact that it's God, man, and then anything else that you want to put below is fine.
Okay.
But government wants to be above God. They want to dilute God. They hate God. They want to be in charge of you. They're not in charge of me. I don't consent to any of their bullshit. Right. So the way they get you is you're spinning out of control, lost in space. You're insignificant. We're running out of resources. We're running out of water. Where the star's going to blow up. An asteroid's going to hit us. The nuclear bombs are going to hit us. Right. All of that is bullshit. All of it is complete and total bullshit. And they want us living in fear as their slaves on their farm. If you play on their ball field, you have to play by their rules. If you play with their fiat money, you have to play by their rules. Right. So when you unplug from the system and stop feeding the nonsense that they're teaching us, then you unplug and you go back to, what this world is. I walked away, you asked the money question. I was making a large 6-figure number. Okay. And I walked away from it all, right, to just do this. So yeah, this is all I do. This is what I do all the time. So what do I get out of it? I'm waking up my fellow man. I'm freeing people from the matrix. There's tons and tons and tons of people waking up, and nobody goes back once they see it. Once they see it, nobody goes back.
Actually, they do. I've talked to a lot of people that were flat earthers and then apologized to their friends and family that they alienated after they went into flat earth. But then I guess
that's not true. That's not true. You talk to people that claim they were flat earthers. Nobody was a flat earther. And
no true Scotsman, right?
No, nobody goes back. Nobody goes back.
Right.
These are
no
the
true
people,
Scotsman argument.
These are people that are waking up to flat Earth, right?
Well, then ask me this. Dave.
Check out my Roseanne Barr podcast. Right?
Roseanne Barr is a really good person to talk to about flat Earth and basically anything else. But then my question to you, Dave, is I've got to get up and go to work tomorrow, and I've got to do research in the lab. Well, that's great. I've got to submit papers, and I've got to make a living through my justification of science. Why have I not seen a reality show of all of the flat earthers getting on a boat and finding this magical ice wall that you guys talk about that you put in your little app here?
What do you mean magical ice wall? You haven't seen the ice wall? You haven't seen the shoreline of Antarctica? Is that what you don't believe?
We can map out the outline of Antarctica, right? It's an island.
No, who circumnavigated? Captain Cook was the last person that tried to do it. It took him 3.5 years. He went over 68,000 miles. Okay,
this is behind. Are you associated with Mark Sargent?
68,000 miles. Check this out. This is the average height of all the continents. Which is the highest continent in the world? Antarctica, by more than double. Right? Antarctica is the shoreline of our world. It is the containment of our waters. What's beyond Antarctica? I don't know. I think there's more land, but we don't need to go beyond Antarctica to prove that. Yeah, you
do. Yeah, you do.
No, we don't.
If you're gonna say that the Earth is a flat disk, you have to go past there. You have to show us
because the journey of Magellan. That took the better part of. They left with a crew of 3 ships, and almost everyone died, and barely anybody came back.
What are we talking about?
The Cook expedition was a single he did it, and it was no problem.
Yeah.
The what? No.
The circumnavigation around Antarctica, it was a very doable expedition. Yeah.
So I actually have that right here.
What you're showing is the side of an iceberg. That's it. That's all you're showing.
No, I'm showing you the shoreline of Antarctica. So
yeah.
So here's an encyclopedia, right? That it shows it's from 1954, and it talks about the I think this was the trip you're talking about. It took 22 days, right? And so where did they go? They went from Deception Island over to Little America, which I go back to here. Right. So when they went, these are the research bases on the flat Earth map. This is where they all are. Right. And so they went from base to base to base. Right. And here it says that the expedition made extensive flights covering all of the Antarctic coasts. Went all of the Antarctic coasts. They didn't go to the center. Right.
There are people in Antarctica right now.
There are people. There's actually way more than you actually think, right? So this is where they went. They went from here, right? Then they went over to they went to this other spot over here, I think, right? And then right there. Then they went over where they call the base, what they call Little America. Then they went from there. No,
I don't mean to interrupt you. But why are you showing us the globe version of Antarctica if you don't believe it? I'm showing
you because I'm showing you what they're claiming they did and what they actually did, because I'm going to show you. So they went to the South Pole, the center, and then they went back there, right? But if we look at this, what it really is this, okay? So here's where they were. They went there to there to there to there. And you look at that on just a possible flat Earth map, they went from here. This is where they went. They went from here to here to here. Now that's as big as South America. That's a massive trip, right? Here to here to here. What's out here? We don't know. This is all they did. They went from here. They said that's the South Pole. It's not. And then they went from here and they went from there. That's all they did.
I disagree with all of the things you just said, because that's not how, because it's not how reality works. But I'll ask you, if somebody's already given the flat Earth movement a $20,000 laser gyroscope that immediately when they turn it on, pegged the rotation of the Earth to 15 degrees an hour. And then
so you're watching Netflix on a hit piece that was highly edited, and you don't take the time to go look at what actually happened, right? So I'll tell you what actually happened. The ring laser gyro, it measured about a 15 degree per hour drift. And then Bob,
matches the rotation of the Earth.
Bob, off camera, mic on, said, "We're not done. We better not give the Globers this information because they're going to run with it before we complete." Then they said, "Okay, well, is that the Earth rotating or is that the ether rotating?" And they said, "Well, in another experiment we could do at the same latitude, we can go up the Pikes Peak or whatever the name of the peak was, 10,000 feet high, and we could do another measurement." And they measured it, and it was a significant difference that can only mean that. Hold on, that is conclusive proof that it's not the Earth spinning, that it's the ether spinning. But they left that out of the movie. And then
that ether experiment you're talking about was debunked back in, what was it, the 1800s, Sean? The
early 1900s.
Michelson-Morley experiment.
Late 1800s.
Yeah, they went out to measure the flow of the ether around the Earth, and it does not exist.
Yeah, but that's incorrect. The ether used to actually be on the periodic table. They took it out because they need to get rid of the ether to have their heliocentric nonsense, right? But we're not testing for the ether. That test proved it wasn't the Earth spinning. Okay, and so you say that Michelson-Morley was debunked. I disagree. I'm not the guy to argue that. You got to talk to Austin Whitsitt. He's gone down that road. He's destroyed that argument a million times. That's not my specialty, so I can't speak there from a point of knowledge.
I need to see the data.
Yeah, I agree. See, John and I are scientists, and you guys just say, "Well, we nailed it," but you never release the data. You just keep saying that nobody will believe you.
So here on my app, if you go to the homeschooling page, there's a section called.
You have a homeschooling page on your app.
Yep,
I just want to be very clear that bothers me.
Why does that bother you?
Because homeschool children should not be exposed to this information.
Oh, absolutely. They totally should. The kids that are exposed to this, they're doing so well. It's amazing. There's a part called Schooling Globers. Where the heck is it? Homeschool. It didn't show up. There's a section called Schooling Globers, and it'll blow your mind. Oh, there it is, right here. Schooling Globers. If you go to that page, there's all of the stuff, all the things you're talking about, which will show up. And there's long. The problem is the lectures are like 3 hours, so you really have to want to know this information to learn it. Belief is the enemy of knowing. You believe the sun is 93 million miles away, and because they measured it when Venus transited the sun, and Venus is the same size as Earth, which is an assumption, they falsified the radius, right? You believe that because you were told it. You've never verified it yourself, right?
And you haven't verified any of these things you're telling me. You're throwing out the same type of arguments that you say, That's not true. I just believe, but you can't verify any of this.
I showed you that I showed you the frozen lake earlier, and you just didn't have an answer, or you said refraction, right? With the lights on the
frozen lake.
Didn't I show you the frozen lake?
Are you telling me what are we talking about?
We're talking about.
You didn't show us any frozen lake. You showed me that they apparently walked
I didn't show you this. So this is a lake, right? And so we got a guy out there, camera 6 inches off the lake. He put these lights out there at 8 miles, 7 miles, 6 miles, and 5 miles. Now, the Earth is so big, you're not going to notice that. But at that distance from that height, the curvature should have been over 30 feet, over 22 feet, over 15 feet, and over 9 feet. But somehow all of the lights showed up on the same line.
What line? What line is that?
This line right here, this level line, this horizon line, they all showed up there. They all refracted up the exact amount they needed to trick you that the Earth was flat, right? Cold, dark, no humidity, frozen lake, large bodies of water at rest lie flat, and they freeze flat when they're still. And you believe that lake curves 30 feet to this light, 22 feet to this light, 15 and 9. Right? But for some reason, they all show up and they're all in view. This falsifies a physical horizon. This shows you that the Earth is flat. Well, it's not big enough. We've done all over Lake Balaton. We did 27 miles with a laser, 27 miles, and we could see it. We could see it. That is plenty of distance, but there is no curvature. If something doesn't
see a laser at 27 miles,
no, this isn't a laser. This is a light. This is not a laser. This is a light, okay? This is just a light, and we can see the source of the light. If something doesn't curve, then it's what?
It could be falsified.
If something doesn't curve, I'm just asking you a question.
I'm telling you an answer.
No,
you're showing me a picture.
You're
showing me a picture of 4 lights on a hazy image, and you've labeled them with numbers and everything.
Would you like to see the video? Do you want to watch the video that shows the whole documentation of it? I'm just showing you some stuff. If you want to learn that stuff in the app on the experiments section, all of the experiments are done there. All of the observations are done there. It's all done. It's all organized for you to take the time to see. I'm just showing you a snapshot of it. Don't believe this picture. If you believe this picture, that's ridiculous. But answer the question. If something doesn't curve, it's what?
It could be parabolic. It could be,
no,
refractory.
Parabolic's curved. If something, I'm just seeing how genuinely honest you can be. If something doesn't curve, then it's what?
It would be flat.
Okay. And if something doesn't move, then it's what?
There's a lot of reasons for that.
If something doesn't move, what can you definitively say about it? If something doesn't move, if something's not moving, then it's stationary. That's the answer. Okay. Here's the thing.
But see, Dave, I understand that you want to make me say the Earth is flat because you said if something is curved, it's flat.
I'm not telling you to say that. I just wanted you to understand.
But what I'm saying is that your scientific experiments that you say that take 3 hours of video to prove are not repeatable, and they are not.
That's not true. You haven't even watched them. How could you say they're not repeatable? Not true. And how do you even know they're experiments? I was saying there's lectures on this stuff, right? There's pilots that will tell you that the Earth is flat. There's the whole seasons thing. We didn't even go there.
If that's true, if all that you're saying right now is true, if I could go to you're saying there's pilots, like that means there's a few. That means
there's a ton.
Why is this? Then why is this such a thing that only a handful of people on the internet, like yourself, do?
A handful.
To make a living?
Blue dots.
Huh?
There's a ton of people. They did a poll like 4 or 5 years ago in Brazil. 11 million people in Brazil, flat Earth, right? But here's the thing: they're not going to put
that has absolutely no context. Do you understand what I'm saying? You're saying things that have no context.
They did a survey in Brazil. They said
11 million people out of how many?
11 million out of, I don't know how many people are in Brazil. That's a good question.
There you go. There's the context you needed.
But it doesn't matter. When you say how come there's a handful, is 11 million in Brazil a handful? Right?
Depending on if there's 300 million people sitting in Brazil, yes, it's a handful compared to the population size.
So there's tons and tons of people, more and more waking up every day. Bigger and bigger podcasts are starting to talk about it. Candace Owens is ready to talk about it. Tucker Carlson's almost ready to talk about it. Hey, and yes, your favorite Alex Jones, he's already talked about it.
Actually, he doesn't. I actually pay attention to Alex Jones because I feel like his rhetoric.
Did you see when I was on Alex Jones?
I did not, and I'm actually kind of mad I missed it.
You can look it up. Just go on my channel.
I'm sure
it's Alex Jones.
I will. And the reason I pay attention to Alex Jones is because I believe his rhetoric is just as dangerous and counterproductive as your rhetoric.
Right.
And that's the reason that this is a problem.
I got it. I'm sure you're fully boosted and vaccinated. You don't have to tell me it's a personal question, but I'm pretty sure.
Oh, I've seen your Twitter. I understand what you think about the shot and the clot shot and the coronavirus.
All
Yeah.
right.
And that's and if I was to ballpark it, I would guess that's what you talked to Alex Jones about.
No, I didn't talk to him about that. No, we talked about flat Earth.
He let that happen because he doesn't like Johnny Bravo to talk about on his show.
Eddie Bravo was on.
Eddie Bravo, sorry.
So, I was on twice.
Then that makes sense. There we go.
In his studio a couple weeks ago, and check it out. It's Alex is a tough cookie, but
yeah, it's tough. He owes $1 billion, almost $1.5 billion to San Diego families.
Yeah, but they're willing to settle for $83 million, and he's not going to have to pay a penny, right?
I don't think that's how it's going to work out.
Yeah, well, there's other things that you can look into. Another place to look for these things that aren't flat Earth, stoplookthink.com, and you'll find out all of these other things, especially the one that you keep bringing up, that they're not what you think it is. Dangerous to talk about, question the authority of the government, but stoplookthink.com.
I don't think I mentioned the government at all today. I don't think we did. But the problem I have is that science literacy is a real problem in America right now. And discussions, pushing thoughts and unverifiable ideas like you do and Alex Jones does is bad. And I'm not saying that you're a bad person for doing it. I just wish that, you had the science, like we would teach better science literacy earlier in schools so that people, before they're called Flat Earth Dave or Flat Earth Diane, they're, included into the bigger science community and can make a real contribution instead of just spouting these falsehoods into YouTube.
You're saying science literacy is if you repeat and regurgitate what the Rockefeller funded textbooks tell you. Okay, that's what if you want to become a scientist, you have to memorize and regurgitate, and not question. Right? That is it in cosmology. If you go against what the mainstream says, if you look into our old world, have you looked into the old world yet? Into what was here 150 years ago? You think it was the Wild West. It was not. There was an advanced civilization here. Advanced.
Yeah. This is good stuff. Yeah. I was kind of afraid we get here because that's the kind of conspiracy adjacent stuff I would expect if you went on Alex Jones's website or on show. And I'm sorry I missed it because I do pay attention to Alex Jones.
It's on there. It's on the
I'm sure it is. I can't believe I missed it.
Go to my interview section. It's right there. And then while you're on my website, there's a banner that says Old World Order. Watch that video.
And I'll also pick up one of the Flat Earth Smackers, your $149 pickleball paddle.
They're awesome.
Yeah, great. See, I understand why you're doing this, Dave, but it bothers me that.
How do you understand? I do it for the money? Is that why I'm doing it? Is that what you understand?
Is
that why I'm doing it? Is that why
you are espousing easily disprovable things on your YouTube page? And if you're getting into COVID territory, which I'm sure you did, I don't want to talk about that right now because it's not the topic of this. I understand that this is what you do. This is your thing. And
Justin, I'm just saying, would you be interested in having a higher level conversation with another one of our guys? Very respectful, Austin Whitsitt.
Probably not, because this is wearing me out right now, even having this conversation with you, because I understand where you're coming from. And I get it. It's fine. I mean, I'm not saying you're a bad person for doing this. I'm just saying that if you're going to, and everybody should make a living how they want to make it, but it does explain a lot if you went on Alex Jones's website or show and espouse this stuff, because that's the kind of adjacency to complete nonsense that I associate with flat Earth.
Okay. Well, that's your opinion. You're right to it. But one day you will see. One day. That day is not too far away.
I would probably be sooner to believe the Hollow Earth than the Flat Earth, because those movies were good in Godzilla. That's a more entertaining Earth for me.
So you're on a spinning ball flying through an infinitely possible space vacuum with high pressure gases collapsing, creating stars from nebulas. It's a really cool story, right?
Yeah.
It's a cool story.
It's easily explained.
Yeah.
And it's actually easily explained with freshman or sophomore level physics.
All right, man.
All right. Well, I think they'll probably wrap it up
Thanks.
here. What do you think?
interesting
wanna
conversation.
agree to disagree?
We totally we can disagree to disagree. How's that?
That'll work.
We disagree.
It's still America, Dave.
FlatEarthDave.com. Find out more information. Don't believe anything these guys said, and don't believe anything I said.
Well,
Go verify.
I can edit this video, right?
Yeah, but then
The lethal edit, yeah.
I'm going to put out the whole video. So don't feel free to do whatever you want. So check it out.
I was just joking. I of course don't think John would
I have
edit
the
it
crash
wrongly.
course. I have a crash course. It's a whole bunch of videos that YouTube's hiding from you. Just watch a couple of them. Watch them as comedy. Just say it's comedy, right? And then I guarantee that if you watch 2 or 3 of them or 4 of them, you're going to be scratching your head and wondering how you ever missed it. So,
and for everyone else who wants to learn real science, subscribe to Dr. John's.
all right.
No, that's okay. It was great having you guys both on. I really appreciate it. It's been a pretty riveting
Thanks,
debate.
Justin and John. Appreciate it.
Thanks, Dave. Take care.
Thank you,
right,
guys.
Bye-bye.